Imagine you're in a spaceship, traveling close to the speed of light. You glance at your clock and see a minute pass, but back on Earth, much more time has gone by. This sounds strange, but it's real. It's part of what Einstein called special relativity. It tells us that time doesn't pass the same for everyone, everywhere. Time is not fixed. It bends and stretches depending on how fast you move. At normal speeds, like driving a car or flying in a plane, you won't notice much of a difference. Your watch and the watch of someone sitting still on Earth will stay in sync. But if you could somehow move at a speed close to the speed of light, say 90% of it, your clock would tick slower than someone else's. It's not because the clock is broken. It's because time itself is passing more slowly for you. This is called time dilation. Think of it this way. Light always moves at the same speed. If you're standing still and shine a flashlight, the light moves away from you at the speed of light. If you're moving forward really fast and shine that same flashlight, the light still moves away from you at the same speed. To make that happen, the universe has to make adjustments somewhere else. So it adjusts time. That's the only way to keep the speed of light constant for everyone. So the faster you move, the more time has to stretch for you. Let's say there are two twins. One stays on Earth. The other travels in a spaceship near the speed of light for several years and then comes back. The one who stayed on Earth aged normally. The one who traveled aged less. They come back younger than their twin. This isn't a story. It's how time actually behaves when you approach the speed of light. Scientists have tested this. They've taken atomic clocks, very accurate ones, and flown them on airplanes. When they compared the flown clocks to ones that stayed on the ground, they found a difference. The moving clocks ticked slightly slower. This matched what Einstein predicted. So while we don't notice it in daily life, time really does slow down when you move faster. It's not a trick or illusion. It's built into the way the universe works. Time does not move at the same rate everywhere. Gravity affects how fast or slow time passes. The stronger the gravity in a place, the slower time moves there. This idea comes from Einstein's theory of general relativity. It's not just a theory on paper. It has been proven through experiments and observations. Think about a clock on a mountain and a clock at sea level. The clock on the mountain ticks slightly faster. That's because it's farther from the center of the Earth, where gravity is weaker. The clock at sea level is deeper in Earth's gravity well, so time moves slower there. The difference is small, but we can measure it. GPS satellites, for example, orbit above Earth, where gravity is weaker. Their clocks run a bit faster than clocks on the ground. Engineers have to adjust for this difference to make GPS accurate. Without that fix, GPS would drift by several kilometers each day. Now picture a spaceship flying near a black hole. Black holes have extremely strong gravity. If a crew orbits just outside the edge, time for them would move much slower than for someone far away. If they spent a few hours near the black hole and then returned, they might find that years had passed elsewhere. This is not science fiction, it's physics. Scientists call this time dilation. The same rules apply to all massive objects, not just black holes, but the effect becomes stronger as gravity increases. Even here on Earth, time dilation from gravity is at play. An atomic clock placed in a basement will tick slower than one on the top floor of a building. Again, the difference is tiny, but it's there. That means the flow of time is not absolute. It's tied to where you are and how strong gravity is around you. Airline pilots, astronauts, and physicists all deal with these effects. The International Space Station orbits Earth at high speed and altitude. So clocks on board tick differently than those on the surface. These shifts are predictable and manageable, but they matter when precise timing is required. Time feels steady in daily life, but it bends and stretches depending on gravity. That's the strange but real relationship between time and space. Imagine you're on a spaceship traveling close to the speed of light. You're sitting in your seat, flipping through a book, or maybe just staring out into space. Back on Earth, years are passing. People are getting older. Clocks are ticking away. But for you on the ship, time is passing more slowly. Your heart still beats. You still think. But everything slows down from the point of view of someone watching you from Earth. This isn't science fiction. It's how time really works when you move fast. This idea comes from Einstein's theory of relativity. When you move quickly, especially at speeds near the speed of light, time stretches. This is called time dilation. It means time moves slower for you than for someone who is not moving or who is moving more slowly. The faster you go, the more this effect grows. But even on Earth, time dilation happens. It's just so small that we don't notice it. Take GPS satellites, for example. They're orbiting the planet at high speeds. Because of their speed and their position above Earth's gravity, the clocks on those satellites tick just a little bit slower than clocks on the ground. Engineers have to correct for this. If they didn't, GPS directions would drift off by several miles each day. You can also think about astronauts. If someone were to travel far into space at near light speed, they could come back to Earth to find that decades have passed here, while they only aged a few years. This is sometimes called the twin paradox. One twin stays on Earth. The other flies in a fast spaceship. When they meet again, they find they're no longer the same age. The one who traveled is younger. Time dilation doesn't mean you feel anything strange. On the fast-moving ship, everything would seem normal. Your watch ticks like always. Your body ages at its regular pace from your own point of view. It's only when you compare your time to someone else's that the difference shows up. This isn't a trick or a glitch. It's built into how time and space work. The universe keeps things consistent by changing time and distance when you move fast. It's not just theory either. It's something we've measured, tested, and use every day without even realizing it. Time passes more quickly on a mountain than at sea level. That might sound strange, but it's a real effect. It's not something you can notice with your watch, and you won't feel any different, but it's happening all the same. The reason for this has to do with gravity and how it affects time. Gravity pulls everything toward the center of the Earth. The closer you are to the center, the stronger the pull. Sea level is closer to the center than a mountaintop, so gravity is a little stronger there. According to general relativity, stronger gravity slows down time. That means time moves a bit slower at sea level than it does up on a mountain. This is not a theory in the casual sense. It's a tested scientific model with measurable effects. Let's say you place two atomic clocks, which are very precise, different locations, one at sea level and the other on top of a mountain. Over time, the clock on the mountain will show a slightly later time than the one at sea level. The difference is small, only a few nanoseconds over the course of a day, but scientists have measured it. For example, clocks placed at the top and bottom of a tall building will tick at slightly different rates. The higher one runs faster. GPS satellites rely on this fact. They orbit above the Earth where gravity is weaker. Their clocks tick faster than clocks on the ground. Engineers had to build in corrections for this, or the system would give inaccurate results. Even a small time error would cause location mistakes by several meters. So this isn't just theoretical. It has practical impact on things we use every day. Imagine living in a cabin high in the Rockies while your friend lives at the beach. Over the years, your clocks would drift apart, even though both are working fine. It would be like time is stretching just a little more up there. You wouldn't notice the change, but if you compared notes after many years using sensitive equipment, the difference would be there. This time shift is tiny, but it shows how the world works in ways we don't always expect. What seems solid and fixed, like time, can stretch and bend depending on where you stand. GPS satellites rely on precise timekeeping. To give accurate location data, they must track time down to billionths of a second. Even a tiny shift can throw off the whole system. That's why these satellites must adjust for relativistic time shifts, differences in how time passes depending on speed and gravity. Two effects from Einstein's theory of relativity matter here. One comes from special relativity. The other comes from general relativity. Special relativity says that time slows down for objects moving fast. GPS satellites move around Earth at about 14,000 kilometers per hour. Because of that speed, their clocks tick more slowly than clocks on Earth. But there's another factor. General relativity says that gravity affects time too. The closer you are to a strong gravitational field, the slower time passes. Since GPS satellites orbit far above Earth, they experience weaker gravity than people on the ground. That makes their clocks tick faster than those on Earth. These two effects don't cancel each other out. In fact, they add up in a way that matters. The weaker gravity speeds up the satellite's clock by about 45 microseconds per day. The high speed slows it down by about 7 microseconds per day. So in total, the satellite's clock gains about 38 microseconds every day. That might not sound like much, but it is. GPS works by measuring how long signals take to travel from satellites to a receiver on the ground. The system needs to know exactly when each signal was sent. A clock error of just a few microseconds can cause a location error of several kilometers. If the satellite clocks gained 38 microseconds every day without correction, GPS would quickly become useless. Engineers deal with this problem in two ways. First, they adjust the clock rates before launch so they run slightly slow. Once in orbit, the time dilation from speed and gravity makes them tick at the correct rate. Second, the GPS control segment on Earth keeps checking satellite clocks and correcting them if they drift. This ensures long-term accuracy. This setup lets GPS receivers on Earth calculate their position within meters. Without accounting for relativity, that wouldn't be possible. The present isn't a solid point in time. It's more like a short window, just a few seconds long, where we feel grounded in what's happening right now. Our brains stitch together sensory information and memory to create this feeling of the now. But what we call now is already slightly delayed by the time we notice it. You don't feel reality as it happens. There's a processing lag. When light hits your eyes, it takes about 100 milliseconds for your brain to form an image. The same goes for sounds and touch. Your brain gathers this data, holds it briefly, and then lines it up to make a single, smooth experience. That assembled moment is what you call the present. In practice, it's a short buffer of time your brain uses to keep your perception steady. This is why, when a glass falls off a table, you react to the sound and movement as one event, even though they arrive in your brain at different speeds. You hear the crash, see the fall, and maybe feel the vibration through the floor, but it all feels like it happened at the same time. That's your brain syncing things up. It groups input into a 2 to 3 second window and treats that window as the now. This short window also shows up in how we speak. A single sentence usually lasts around that same span of time. It's the chunk we can hold in working memory. Ask someone to recall a phone number or a phrase they just heard. They can do it if it fits into that brief mental window. Stretch it out too long, and they'll miss pieces or start guessing. Even athletes depend on this window. A tennis player doesn't return a serve by reacting in real time. The ball moves too fast. Instead, they rely on practiced patterns and anticipation. Their brain fills in gaps, predicts movement, and smooths it all into what seems like quick reaction. That's still the present at work, an edited, synced-up version of reality that feels smooth even when it's not quite accurate. You don't live in a single moment. You live in a stitched-together stream of near moments, carefully assembled by your brain to feel like now. Light from the sun takes about 8 minutes to reach Earth. That might sound quick, but it tells us something important about the scale of space and the speed of light. The sun is about 93 million miles away from Earth. Light travels at about 186,000 miles per second. When you divide the distance by the speed, you get a time delay of just over 8 minutes. This delay means we never see the sun as it is right now. We always see it as it was 8 minutes ago. If the sun were to go dark this instant, we wouldn't know until 8 minutes later. The same goes for anything that happens to the sun: solar flares, bursts of radiation, or any sudden change. We experience it 8 minutes after it occurs. This idea applies to other objects in space too. The farther something is, the older the light we see from it. The moon is closer, about 240,000 miles away. Light from the moon takes about 1.3 seconds to reach us. If you stand outside and look at the moon, you're seeing it not as it is, but as it was a little more than a second ago. Now think about a more distant star. Say it's 10 light years away. That means its light takes 10 years to reach us. If something dramatic happened on that star, we won't know about it until 10 years later. In this way, looking out into space is like looking back in time. The farther away the object, the older the image we receive. The sun's 8-minute light delay also plays a role in space science and planning. Satellites monitor solar activity to protect electronics on Earth and in orbit. When they spot a flare, engineers know the particles will take longer than light to arrive. That gives them time to react. Light is fast, but charged particles are slower, so that warning can be valuable. Even communication with spacecraft uses this timing. Signals to and from Mars, for example, can take between 5 and 20 minutes depending on the planet's positions. So engineers can't joystick a Mars rover in real time. They set commands, wait for a response, and plan with that delay in mind. Understanding this time lag helps us work with the real conditions of space. The universe is about 13.8 billion years old. That number comes from looking at light from faraway galaxies and from measuring how fast the universe is expanding. Scientists use a concept called the cosmic microwave background to help figure this out. It's a faint glow left over from when the universe was very young. Think of it like the heat left in an oven long after it's turned off. That glow helps scientists know how long the universe has been cooling and spreading out. When we say the universe is 13.8 billion years old, we're talking about the time since the Big Bang. The Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. Everything we now see, galaxies, stars, planets, started from that point. Imagine blowing up a balloon with dots on it. As the balloon grows, the dots move away from each other. That's like how galaxies move apart as the universe expands. We can also think about time in terms of distance. Light travels fast, about 186,000 miles per second. When we look at a star that's a billion light years away, we're seeing it as it was a billion years ago. So telescopes are like time machines. The farther we look, the further back in time we see. Scientists use tools like the Hubble Space Telescope and the James Webb Space Telescope to look deep into space and learn about the early universe. This age of 13.8 billion years is not just a guess. It comes from different sources that all point to the same result. One method is watching how galaxies move away from each other. Another is measuring elements like hydrogen and helium. These formed in the first few minutes after the Big Bang. By understanding how much of each element exists, scientists can figure out how long the universe has been changing. Even though 13.8 billion years sounds like a huge number, it's not forever. Stars and galaxies form and die within this time. Our own solar system formed about 4.6 billion years ago, which means it's only been around for a third of the universe's life. If the universe were a calendar year, Earth would have shown up in early September. Humans wouldn't appear until the very last minutes of December 31st. That helps put things in perspective. Black holes are places in space where gravity is so strong that nothing can escape, not even light. But gravity doesn't just pull things in, it also affects time. Near a black hole, time slows down. If you were to float close to one, your clock would tick slower compared to someone far away. This isn't science fiction, it's part of Einstein's theory of general relativity. Let's say two astronauts are part of the same mission. One stays in orbit far from a black hole. The other takes a ship down close to the event horizon, the point of no return. For the astronaut who stays back, a week goes by. But for the one near the black hole, only a few hours pass. If they reunite later, the astronaut who stayed far away would have aged more. The closer you are to the center of the black hole, the more extreme this time difference becomes. At the very edge, time almost stops from the point of view of someone outside. That's what it means to say a black hole can warp time to a near standstill. This isn't just an idea. It matches what we observe in space. When we watch stars or gas move around black holes, they behave in ways that suggest their time is ticking slower. We even see redshifting, where light stretches out and shifts toward the red end of the spectrum. This happens because the light is climbing out of a deep gravity well, losing energy along the way. That's another sign that time is moving differently there. You wouldn't notice the change in time if you were the one near the black hole. Your watch would tick normally, and your heartbeat would feel the same. But someone watching you from far away would see everything you do happen in slow motion. That includes light leaving your ship. It would stretch out and dim. From far away, it might look like you're frozen. We've tested this kind of time shift on Earth, too. Atomic clocks placed on airplanes or in tall buildings tick at different rates than those at sea level. The difference is tiny, but it's real. A black hole just takes that effect to the extreme. It's not magic, it's physics. Gravity, stretching space, and slowing time. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape. At its center lies a point called the singularity. This is where all the mass of the black hole is compressed into a single point. The laws of physics as we know them break down here. One of the strangest ideas about the singularity is that time stops. This doesn't mean clocks just pause. It means that time itself, the thing that allows events to happen one after another, comes to a halt. To understand why, think about how gravity affects time. According to Einstein's theory of general relativity, gravity slows down time. This has been tested. For example, satellites in orbit need to adjust for time running slightly faster in space than on Earth because Earth's gravity slows time a little. Now take that idea and push it further. The stronger the gravity, the slower time goes. Near the edge of a black hole, called the event horizon, gravity becomes extreme. Time slows a lot. If someone hovered near the event horizon and then flew back out, they might find that while only minutes passed for them, years passed for everyone else. That's not science fiction, it's a prediction of relativity. As you go deeper into the black hole, gravity gets stronger and time slows more. At the singularity, gravity becomes infinite. The equations say time stops there. No ticking, no passing moments, no sequence of cause and effect. It's not just a pause. There is no more before or after at all. But there's a problem. We don't really know what happens at the singularity. The math breaks down. Physicists can't describe it using general relativity alone. Quantum mechanics, which describes very small things, doesn't work with the infinite gravity of a singularity. That's why many believe we need a new theory, something that combines gravity and quantum mechanics. Until then, we rely on what the equations tell us. At the singularity, time ends. You can picture it like this. Imagine falling into a black hole. From far away, people see you slow down near the event horizon. You seem to freeze, but from your point of view, you fall right through. As you approach the singularity, you wouldn't see clocks ticking slower. You'd see them stop, not because they break, but because time itself has nowhere left to go. Some philosophers say time isn't real. They argue it's something we made up to understand change. To them, time doesn't exist outside our minds. It's a tool, like a map. The map helps us find our way, but the map isn't the land itself. Let's say you look at an old photo. You might say, that was 10 years ago. But what does that mean? The photo is still there now. You're looking at it in the present. The person in the photo no longer exists in that exact form. Your body has changed. Your thoughts have changed. But the idea of 10 years ago depends on how we mark changes. We measure them in seconds, minutes, hours. Yet those units come from clocks, and clocks are machines we built. So one view is that time is something we invented to make sense of motion and memory. Some thinkers, like Julian Barbour, go further. He says change is real, but time is not. Imagine a film strip. Each frame is a still image. Your brain turns those images into motion when played quickly. According to Barbour, what we call time is just our experience of one frame after another. Each frame exists on its own. The past isn't behind us. The future isn't in front of us. All frames just are. They don't move. We do the moving, through memory, through thought, through attention. This isn't how we normally think. We see the sun rise, then set, and say time passed. But think about the sun from space. It doesn't rise or set. Earth spins. We see different parts of the sky and call that morning or evening. Time, in this view, is a name we give to those changes. It helps us plan and tell stories, but it may not be something that exists outside of human thought. Physics adds to this debate. Einstein's theory of relativity says time isn't the same everywhere. It bends, it stretches. If you fly fast enough or live near a strong gravity source, your clock ticks slower than someone else's. That means time is not fixed. It changes depending on where you are and how you move. If time were a solid, independent thing, it shouldn't behave that way. Even our own lives show cracks in how we understand time. When you're waiting at the doctor's office, 5 minutes feels long. When you're on a walk with someone you enjoy, an hour feels short. The clock doesn't change. You do. That suggests time isn't something outside you. Ticking away no matter what. It may be inside you, something your mind uses to order events, store memories, and predict what might come next. Eternalism is a way of thinking about time. It says that all moments, past, present, and future, exist at once. They are not flowing or passing. Instead, they are all laid out, like pages in a book. You might be on one page now, but the others still exist. This view treats time as a dimension, similar to how we think of space. Just as all places exist, even if you're only standing in one, all times exist, even if you're only experiencing this one. Think of a train. Each car on the train holds a different moment in time. You're in one car right now, the present. Behind you are cars with your past. Ahead are cars with your future. Eternalism says all these cars are real and connected, whether you're in them or not. You move through them, but they don't vanish or appear. They just are. This idea often comes up in physics. In Einstein's theory of relativity, time is part of the fabric of the universe. When two people move at different speeds or are near large masses, they experience time differently. From that theory, it's not a big leap to say that all times might exist in the same way that all locations do. You just don't stand in all of them at once. A person might say, "But I remember the past and not the future." Doesn't that mean the past is real and the future isn't? Eternalism would say no. Your brain just works that way. Memory gives you access to the past. You don't have a similar tool for the future, but that doesn't make the future less real. Think of it like your field of vision. You can see what's in front of you, not what's behind. But what's behind you still exists. Imagine a movie on a film reel. Every frame is there, start to finish. You see only one frame at a time when it runs through the projector, but the others still exist. Eternalism treats time like that film reel. Your now is one frame, but all the other frames are still part of the reel. Presentism says that only the present moment is real. The past no longer exists, and the future does not exist yet. According to this view, everything that's real is happening right now. Anything that already happened is gone, and anything that will happen isn't real until it becomes the present. Imagine a person walking down a road. They've passed some houses already, and more are ahead. Presentism says only the house the person is walking past right now is real. The ones behind no longer exist. The ones ahead don't exist yet. The road still exists, but only the part the person is currently on is part of reality. This idea contrasts with two other views. Eternalism says all points in time are equally real: past, present, and future. It treats time like a map, where every location always exists. The growing block theory says the past and present are real, but the future is not. In that view, the past keeps building up like pages in a book, and each new moment gets added as it happens. Presentism rejects both. It holds a strict line. Only now exists. That can feel natural because we live in the moment. We can remember the past, but we can't visit it. We can plan for the future, but we can't jump ahead. From that everyday experience, it makes sense to think the present is all there is. But this view runs into trouble with physics. According to Einstein's theory of relativity, time does not work the same for everyone. Imagine two people, one standing still and one moving fast in a spaceship. Each person will experience time a little differently. What counts as now for one may not be the same for the other. That makes it hard to define a single present that is true for everyone. If there's no single present moment for all observers, then saying only the present is real becomes tricky. Still, presentism appeals to our common sense. We feel rooted in the now. We interact with people in the moment. When someone dies, they're gone. When someone is born, they've just come into existence. These are powerful, simple experiences. They make presentism easy to believe, even if physics suggests the story might be more complex. We often think of time as a fundamental part of the universe. Clocks tick, the sun rises and sets, and we grow older. These changes make time feel real and steady. But some physicists now argue that time might not be a basic part of nature. Instead, it might come from something deeper, something more basic and hidden. To understand this idea, think about temperature. Temperature feels real. You can feel heat or cold, but temperature is not a basic part of physics. At the smallest level, it comes from how fast particles move. When many particles move quickly, we feel heat. When they move slowly, we feel cold. So temperature is not fundamental. It emerges from the behavior of smaller parts. Some scientists think time might work the same way. They look at the smallest scales of space and energy, places where quantum mechanics rules. There, things don't behave like they do in our daily lives. Events don't happen in a clear order. Instead, they occur in a way that doesn't always make sense when you try to put them on a timeline. In this strange world, the idea of before and after might not exist the way we expect. One idea is that time appears only when you look at a system from the outside. For example, if you measure particles inside a box, you might see a pattern that looks like time passing. But inside the box, from the particle's point of view, there might be no time at all. The pattern we see, what we call time, comes from how the parts relate to each other, not from time itself flowing. Imagine a group of musicians playing without a conductor. Each musician listens and adjusts to the others. From the outside, it sounds like a song moving through time. But inside, each player just responds to the group. Time, in this case, comes from relationships, not from a clock. This doesn't mean our everyday experience of time is wrong. It just means that at a deep level, time may not be part of the foundation. Instead, it might be a result of other things acting together, like temperature, or like the music made by many instruments. What then is time? If no one asks me, I know. Augustine wasn't being coy. He pointed to something we all feel. Time is part of our daily experience. We live in it, talk about it, measure it, and try to manage it. But when we stop to explain what it really is, things get harder. Words start to slip. Definitions don't hold up. Most people think of time as something that flows. It moves forward, never back. Clocks track it. Calendars split it into days, months, years. You can be early or late. You can run out of time or waste it. But these are ways we use time. They don't tell us what it is. Imagine you're waiting in line. The minutes feel long. Now picture talking to a friend after a long absence. 2 hours go by fast. The clock measures both the same, but your experience is different. So which is real? The time on the clock or how it feels? Physicists treat time differently. In classical mechanics, time is absolute. It ticks the same for everyone everywhere. But in Einstein's theory of relativity, time bends. It stretches or shrinks depending on speed and gravity. Astronauts on the space station age a little slower than people on Earth. That's not science fiction. That's measurement. Yet even these models don't settle the question. Time, in physics, becomes a coordinate, like length or width. It works well in equations, but it doesn't explain why we remember the past and not the future. Why does time feel like it flows one way? Some thinkers say the flow of time is just how our minds make sense of change. The universe may not have a preferred direction. It may be that time is a human way to order cause and effect. We drop a glass, it breaks. We don't see broken glass leap up and reform. That sense of before and after runs deep in how we think. Still, Augustine's words ring true. Time seems obvious until we try to pin it down. We can point to its marks, but not its source. It's always there, but never in full view. It slips between what we can measure and what we feel, like trying to hold water in our hands. It always runs through. In physics, many of the laws that describe how things move and interact don't care which way time flows. If you filmed two objects bouncing off each other and played the video backward, the motion would still follow the same rules. The equations would hold up. Newton's laws, for example, make no mention of a past or future. Whether you run the clock forward or backward, the math works the same way. This is called time symmetry. The Schrödinger equation in quantum mechanics also shows this. It can evolve a wave function forward in time or backward, and the result still makes sense. Even the equations behind electricity and magnetism, Maxwell's equations, stay valid if you reverse time. There's nothing in the rules that says events must move from past to future. It's like watching a pendulum swing. If you recorded it and reversed the footage, it would still look natural, and the physics behind it wouldn't change. Yet in real life, time feels like it only moves one way. We remember the past, but not the future. A glass can fall and shatter, but it doesn't unshatter. Heat spreads from hot things to cold ones, but never the other way around. This difference comes from something called entropy, which is part of the second law of thermodynamics. Entropy measures disorder. Over time, disorder tends to increase. While the basic rules of physics work in both directions, the world we live in doesn't behave that way. You could imagine a deck of cards. If you toss them in the air, they scatter. That's high entropy. Nothing in physics stops them from landing back in a neat stack. But the odds are so small, it might as well be impossible. That's what gives time its arrow. Not the laws themselves, but the way the universe started out in a very ordered state. So even though many physical laws are time symmetric, we still see a direction because of how entropy behaves. It's not the rules that choose a direction, it's the setup. Time doesn't really care which way it flows, but we do, because we live in a world where broken things stay broken and memories only go one way. Time feels like it moves forward. We remember the past, not the future. We age, we grow, and things change. One way to understand why time has this direction is to look at entropy. Entropy is a measure of disorder in a system. A neat room has low entropy. A messy room has high entropy. Over time, without effort, things tend to get messier. Ice melts, coffee cools, buildings crumble. These changes move in one direction and not the other. You don't see broken glass jump up and become whole again. You don't see smoke return to a cigarette. These are examples of entropy increasing. This increase in entropy is not a law that says disorder must happen fast or always. It says that over time, the total disorder tends to rise. It allows for local drops in entropy if something else takes on more. A fridge cools your food by sending heat into the room. The food gets colder, but the room warms a little. The fridge runs on electricity, which also comes with energy losses. When you add it all up, the total entropy goes up. This one-way path, the tendency for entropy to rise, is what we call the arrow of time. You can rewind a video and it looks fine, but in real life, things don't behave that way. You can see a ball roll downhill and slow to a stop. You don't see it sit still and then roll uphill. The math behind physics often works both forward and backward in time. But in real events, we always see entropy go one way, up. Imagine a puzzle thrown in the air. It lands in a scattered mess. That ness is one of many ways the pieces can fall. There are far fewer ways the puzzle can land solved. The chance of landing in order is so small, it may as well be zero. The mess isn't special, it's just more likely. Even our thoughts follow this arrow. Memory is stored as changes in the brain. That change involves energy use and increased entropy. We don't remember tomorrow because that would need entropy to fall, something that does not happen. What we call now sits on the edge of past low entropy states and future higher entropy ones. The universe began in a low entropy state. Over time, stars formed, burned out, and scattered their atoms. Galaxies spread, heat moved from hot to cold. Bit by bit, the universe became more disordered. That rise in entropy gives time its forward push. It marks the difference between what has been and what will be. Causality gives time its apparent direction. When one thing causes another, it sets an order. A ball rolling off a table happens because someone pushed it. The push comes before the fall. You see the push, then you see the fall. That's how we know which came first. This cause and effect link lines events up. Without it, time would lose its sense of flow. Imagine watching a glass fall and shatter on the floor. Now play that scene backward in your mind. The shards gather and rise into a whole glass, which jumps up to the table. That looks strange because it goes against how we expect things to happen. Our minds reject it. Why? Because it lacks a clear cause leading to the effect. The backward scene breaks the chain we count on to tell us what's real. In physics, most of the basic rules work the same in either direction. If you reverse time in a math formula, it would still hold true. But our daily world doesn't work like that. Ice melts in warm air, but it never unmelts by itself. You can mix cream into coffee, but it never pulls back out. These changes, though allowed by the rules, only go one way. That's because of causality and how it interacts with disorder, or entropy. Entropy is a measure of how mixed up things are. Systems tend to move toward more disorder over time. This is not just a guess, it's a core part of thermodynamics. A neat room gets messy. A hot object cools. These are all steps from order to disorder. Once they happen, you can't undo them without more effort. The arrow of time follows this path, with cause pulling effect behind it. Now picture two dominoes. Knock one over and it topples the next. This is a clear chain. The fall of the second piece depends on the fall of the first. If you know the setup and the timing, you can say which came first. But if you only saw the second domino fall and had no other clue, you might wonder what set it off. Causality gives you that clue. It gives you direction. That's how we live each day. We wake up, we make breakfast, we get to work. Each step builds on the one before it. You don't eat breakfast before getting out of bed. These actions unfold in order, not just because of clocks, but because of causes. Events make sense when they follow from what came before. Even memory works this way. You remember past events, not future ones. You remember burning your hand on a hot pan, so next time you're careful. The burn caused the caution. If that link didn't exist, time would feel scrambled. You'd have no clear idea what should come next. Causality doesn't just mark time, it makes it usable. Kant believed that time isn't something that exists out in the world, like a river or a tree. Instead, he said time is part of how we make sense of what we experience. In his view, time is built into the human mind. We don't learn about time from the world. We bring it with us when we look at the world. Think about how you remember events. You don't just see one thing after another. You understand what came first, what came later, and how long something lasted. That sense of sequence and duration doesn't come from the events themselves. It comes from your mind organizing them in time. Kant said we need time to have any experience at all. Without it, everything would be a jumble with no order. Let's take a simple example. Imagine you're watching a ball roll down a hill. You see it start at the top and then move to the bottom. You know it didn't just appear at the bottom. You understand that motion happened over time. According to Kant, your mind adds that sense of flow. The ball moving isn't enough. You have to place each moment in a sequence. That's time, and it's not coming from the ball. It's coming from you. He called time a form of intuition. That means it's a basic part of how we take in the world. Just like we see objects in space, we also see events in time. Both space and time are part of how we structure our experience. They aren't things we find outside ourselves. They are ways our mind shapes what we see and feel. This idea changes how we think about knowledge. If time is part of us, not part of the world, then we can't say we know time as it is out there. We only know how we experience it. Kant wasn't saying time is fake. He was saying it depends on us. Without a mind to notice the change from one moment to the next, time as we know it would not exist. Some interpretations of quantum mechanics challenge the idea that time moves in a straight line from past to future. In daily life, time feels like a one-way street. You wake up, eat breakfast, go to work, and come home. The past stays behind you. The future comes next. But when you look closely at the rules that govern very small particles, rules set by quantum mechanics, that simple picture starts to break down. Take the example of the block universe view. In this view, past, present, and future all exist at once. Imagine a DVD. The whole movie is on the disc at the same time, even though you experience it one frame after the next. Some physicists think the universe might work like that. Every moment might already exist, and our sense of time moving could just be how our brains process information. Now consider the many worlds interpretation. This one says that every time a quantum event happens, the universe splits. Say you flip a quantum coin. In one world, it lands heads. In another, it lands tails. Both outcomes exist, but in different branches of the universe. In this view, time doesn't flow. It branches. It's more like a tree than a line. Then there's retrocausality. It's the idea that future events might influence the past. This sounds strange, but some experiments hint at it. One involves entangled particles. These particles are linked. If you measure one, the other knows the result, even if it's far away. In some cases, your choice to measure one particle now seems to affect what happened to the other one in the past. It challenges the usual order of cause and effect. Another scenario is the quantum eraser experiment. In it, you set up a particle to go through two paths. If you don't check which path it takes, it acts like it went through both. If you check, it acts like it went through only one. But here's the twist. You can decide whether to check after the particle has already hit the detector. Your later choice appears to decide the particle's earlier behavior. Each of these cases suggests time might not be as simple as we think. The laws that work for atoms and photons don't always line up with how we experience time. Scientists are still working out what this means, but one thing is clear. Time at the quantum level doesn't always move forward in a straight line. A year feels much longer to a 5-year-old than it does to a 50-year-old. That's not just nostalgia or a trick of memory. It's something many people notice as they get older. Time doesn't actually speed up, but our experience of it changes. We don't measure time with a clock in our minds. We measure it through what we notice, what we do, and how new those experiences feel. When we're young, almost everything is new. Our brains pay close attention. A trip to the store might mean seeing a new kind of cereal, a dog we've never met, or a stranger who says something odd. The day feels full. We're forming fresh memories, and those memories stretch the time. In contrast, adults have seen most of what fills their day before. Commuting, replying to emails, folding laundry, these things repeat, and our brain doesn't spend much energy logging them. That difference in attention and memory gives the sense that time is faster as we age. A child might recall a week as a series of moments: a math test, a new game at recess, pizza for dinner, a scraped knee, a story before bed. An adult might recall the same week as work, errands, the usual. Even if both had the same number of hours, the child's memory holds more detail, and more detail stretches the feeling of time. Another reason is routine. Routine helps us function. It keeps life stable and predictable, but it also makes time blend together. If you drive the same route to work for 5 years, the trips start to feel like one long drive. Nothing stands out. Your brain doesn't need to do much, so it doesn't mark the time. In contrast, taking the new route even once can make that day stand out more. Think about the last time you went on a trip. You probably remember that week more clearly than the 3 weeks before it. That's because the trip broke routine. You paid more attention. You saw new places, ate different food, spoke to new people. The brain kicked into high gear, and those days felt fuller. That's the same effect children experience more often. This isn't just about memory. It's also about how we process change. As we age, fewer things surprise us. A birthday feels like a nice dinner and a card. For a child, it means a new year of life, a party, gifts, attention, and maybe even staying up late. Their brains treat it as a major event. That's part of why it feels like a big marker in time, while adults often say their birthdays sneak up on them. The marker fades. Even technology adds to this effect. We spend more time scrolling and consuming content passively. It fills time, but it doesn't leave much behind. You might spend an hour on your phone and not recall much of what you saw. It's similar to driving a familiar route. You are awake and active, but you didn't encode new memories. Without those, the time feels like it slipped past you. This shift in how we perceive time isn't a failure of focus or an issue to fix. It's how the brain works. The more routine and familiar life becomes, the faster time seems to move. When we experience something new, time feels like it stretches out. This isn't just a trick of the mind. It's how our brains process unfamiliar events. When you're doing something routine, your brain works on autopilot. It doesn't need to pay close attention because it already knows what to expect. So it saves time and effort by skipping over the details. Days blend together. But when something breaks that pattern, say a trip to a new city or even a different route to work, your brain has to work harder to process it all. It pays attention to more details. As a result, your memory stores more information, and looking back, the day feels longer. Take a normal workday. You wake up, get dressed, eat, commute, and do your tasks. By the end of the day, you may struggle to remember what happened between lunch and the meeting at 4. There's nothing unusual to mark the hours. Your brain compresses the memory because it doesn't need to keep the fine details. But imagine you visit a place you've never been. You hear new sounds, see different architecture, eat food with unfamiliar spices. There are moments of confusion, surprise, and curiosity. These force your brain to stay alert. You remember more because your brain treats the experience as worth storing. That's why it feels like time has slowed down. Even small changes can have this effect. Switching up your routine, learning a new skill, or talking to someone you don't usually interact with can all stretch your sense of time. It's not that time moves slower. It's that you remember more of it. The brain creates a denser record, and that adds to the feeling of extended time. This process is tied to how we build memories. Novelty triggers the hippocampus, the part of the brain that helps form new memories. The more the hippocampus works, the more data it stores. When you reflect on the day, that extra data makes the day seem longer. Think of it like a video file. A busy day full of new things is like a video with lots of frames. A routine day has fewer frames. The brain uses those frames to judge how much time passed. People often say childhood summers felt long. That's because everything was new. Once you grow up and repeat the same seasons over and over, the brain starts skipping. To slow things down again, you need to make things new. Boredom makes time feel slower because your brain doesn't have much to focus on. When you're bored, there's little happening to hold your attention. You might be sitting in a waiting room, watching a clock tick. Every second drags. You check your phone, nothing new. You look out the window, still nothing. With nothing engaging your brain, time seems to stretch. This has to do with how we process time. When your mind is busy, it doesn't track every moment. Think about playing a video game or working on a task that needs your full focus. Hours can pass, and it feels like minutes. You're doing something that pulls your attention away from the passage of time. But when you're bored, the opposite happens. You become more aware of time itself. You start noticing small things, each movement of the second hand, every noise in the background. You're not distracted, so your brain starts counting time in more detail. That makes it feel longer. This is tied to how we remember time, too. When you recall a boring event, it might seem short. You'll say, "That meeting was only an hour," even though it felt like 3. But while it's happening, our sense of time stretches. It's your brain filling in the blanks. It has nothing else to do. Let's say you're stuck in traffic. There's no music playing and nothing to look at. The light ahead turns red again. You feel every second. Now imagine the same delay, but you're listening to a good podcast. Your attention is split. The delay doesn't feel as long, even though it takes the same amount of time. People try to fix this with distractions. They scroll on their phones or talk to someone. These things help, but not always. If the distraction doesn't fully engage your brain, you still feel time dragging. Watching a dull TV show can feel almost as slow as doing nothing. Your brain knows it's bored. Boredom signals that your brain needs input. It doesn't mean something is wrong, just that you're not giving your mind enough to work with. When that happens, time slows down, not in reality, but in how it feels to you. You're driving down the highway. Everything looks normal and you're focused on the road. Then a car swerves into your lane. In that moment, it feels like time slows down. You see the car drifting over, you check your mirrors, your hands tighten on the wheel, and you steer away, all in what feels like slow motion. But when you think back, the whole thing took only a few seconds. That feeling of time stretching out is common in emergencies, and adrenaline plays a big role. Adrenaline is a hormone your body releases when it thinks you're in danger. it kicks off what's called the fight or flight response. Your heart beats faster, your pupils widen, your breathing speeds up, and your senses become sharper. Your body gets ready to either face the threat or escape from it. This surge of adrenaline also changes how your brain handles time. The brain doesn't actually slow time down. What happens is that it takes in more details than usual. You notice more things. Your memory works harder and faster. Your brain lays down more information per second than it does during a normal situation. Later, when you look back, it feels like more time must have passed to hold all those memories. So your brain fills in the blanks and stretches out the timeline. A good way to picture it is like taking slow motion video. The camera doesn't change real time. It just captures more frames per second. That gives you a smooth, drawn out replay. Your brain does something similar when adrenaline floods your system. It picks up more frames. You think, react, and remember more. Soldiers, firefighters, and first responders often talk about time feeling slower during tense situations. Some describe being able to think clearly while everything around them is chaotic. That's the effect of adrenaline, sharpening their senses and speeding up their reactions. It doesn't give them more time, it just gives them the feeling of it. Even people in everyday life experience it. A child falling off a bike, a person slipping on ice, or someone reacting to a pot boiling over. They all might describe the same thing. It happened so fast, but I saw everything. Their brain hit record at a higher rate, packing more into the moment. Memories help the brain reconstruct time. Without them, time becomes slippery. You wake up, go about your day, and it passes. But later, you might not be able to say much about it. You know it happened, but you can't say when something occurred or what came first. Days blur. That's what life is like when memories don't stick. Your brain doesn't store time the way a clock does. There's no internal ticker logging the seconds. Instead, the brain uses events. If you remember a birthday party, you might recall the cake, the candles, and someone singing off-key. Those details act like anchors. They help place the memory in a rough order. If you then remember moving into a new apartment after that party, your brain arranges these two events as before and after. The memory creates a timeline. When you form memories, your hippocampus plays a key role. It's not just storing information. It's helping your brain link one moment to the next. If you're in a car accident, your brain tags it as important. You'll likely remember what you were doing right before and what came after. These connected pieces build a sequence. Without that sequence, the day might feel like a series of still images out of order. This is why routine can make time feel fast. If every day looks the same, your brain doesn't save much from each one. There's less material to form a timeline. You look back on the week, and it feels like it vanished. But if something different happens, a meeting that goes wrong, a surprise visit from an old friend, those moments stand out. They become markers. People with memory disorders often struggle with time. Ask someone with Alzheimer's if they took their pills this morning, and they might not know. Not because they forgot the pills, but because the brain can't place the act in time. It's like the memory exists, but the clock is missing. In those cases, memory and time drift apart. If you've ever traveled, you might have noticed how the first few days felt long. Everything was new. Your brain worked harder to take it in. Later, the trip might seem shorter in memory. That's because your brain compressed the experience. It kept the key parts and smoothed the rest. Again, it's using memory to shape time. Our internal clock tells our body when to wake up, eat, sleep, and carry out daily tasks. This clock lives in a small part of the brain called the suprachiasmatic nucleus. Scientists often shorten this to SCN. The SCN sits in a deeper area of the brain called the hypothalamus. It works like a control center. It keeps track of time using signals from light and other cues from the environment. Light enters the eyes and hits special cells in the retina. These cells don't help us see in the usual sense. Instead, they sense how much light is around us. They send that information to the SCN. When the SCN gets this light signal, it knows it's daytime. When there's less light, it knows it's time to wind down. This process forms what's known as our circadian rhythm. Circadian means about a day. This rhythm runs on a 24-hour cycle, but it doesn't stay exact without outside help, without sunlight or social cues. People can start to drift off this rhythm. They might stay up later each day or wake up at odd times. The SCN keeps our body systems in sync. It tells the pineal gland when to release melatonin. Melatonin is a hormone that makes us sleepy. The SCN also helps the liver, heart, and other organs know when to be active. For example, your body digests food better at certain times of the day. Your blood pressure and temperature also rise and fall in a steady cycle. When you cross time zones or work night shifts, your SCN can fall out of step with your new schedule. This is called circadian misalignment. Jet lag is a common example. You feel tired at the wrong times because your SCN still runs on your home time. Over time, the SCN can adjust to a new light-dark cycle, but it doesn't happen overnight. In fact, it may take several days. One way to help the SCN stay on track is to follow regular habits. Go to bed and wake up at the same time each day. Get sunlight in the morning and avoid bright light at night. These simple actions help the SCN keep your internal clock steady. Jet lag happens when your body's internal clock doesn't match the local time at your destination. This clock, called the circadian rhythm, runs on a roughly 24-hour cycle. It controls when you feel sleepy, when you wake up, and when your body releases certain hormones. It works best when your sleep schedule stays the same every day. When you fly across time zones, especially more than 3, your body can't keep up. It stays on the time zone you left, which creates a mismatch. For example, if you leave New York at 6 p.m. and land in London at 6 a.m. the next day, your body still thinks it's 1 a.m. That means you might feel ready for bed just as the day is starting. You'll probably feel tired, foggy, or irritable. You might also have trouble sleeping at the right times or feel hungry at odd hours. These are all signs that your internal clock is out of sync with your surroundings. Jet lag doesn't hit everyone the same way. Flying east tends to be harder than flying west. That's because it's easier for most people to stay up later than to fall asleep earlier. A westward flight gives your body extra hours, which fits better with its natural rhythm. Eastward travel shortens your day, forcing your body to adjust faster than it wants to. Your symptoms also depend on how many time zones you cross and how well you sleep during travel. A 3-hour shift is easier to manage than a 9-hour one. If you sleep poorly on the plane or during the first night, the effects can last longer. People often try to fix jet lag by drinking coffee or taking sleeping pills. These can mask the symptoms, but don't reset your clock. Exposure to light at the right time helps more. Natural light in the morning can help you adjust when flying east. Evening light works better when flying west. That's because light is one of the strongest cues for your body's clock. Melatonin, a hormone your body makes at night, also plays a role. Some travelers take melatonin supplements to help signal sleep time earlier or later, depending on their direction. Jet lag fades as your body adjusts, but this can take several days. The rule of thumb is 1 day per time zone crossed, though some adjust faster. Athletes, pilots, and frequent travelers often have strategies to speed this up. These might include shifting sleep schedules before travel, getting sunlight at key times, or staying awake until local bedtime on arrival. Time doesn't always feel the same when you're dreaming. You might fall asleep for 10 minutes and dream something that feels like it lasted hours. Or you might sleep for an hour and have a dream that flashes by in a second. This mismatch between real time and dream time is common. It shows that our brains don't process time the same way when we're asleep. During sleep, especially in REM sleep, the brain stays active. This is when most vivid dreams, but the brain isn't following the same signals that it uses when awake. It doesn't check the clock. It doesn't get feedback from the body in the same way. So it makes its own version of time. That version can stretch or shrink. Say you dream you're walking through a city. You take a train. You wait for it. You walk upstairs. You see the sky change from day to night. It all feels slow, drawn out, like you spent hours there. But in real time, that dream may only take a minute. The brain builds a detailed scene, one step at a time, and fills in gaps. It gives the sense that time is moving forward, but not based on real time. Instead, it draws from memories and imagination. There are also cases where people dream in fast cuts, like quick scenes jumping from one to another. This kind of dream might feel short, but contain many images or ideas. It could show someone running, flying, then talking to someone in a strange place, all in what feels like a blink. The brain skips transitions. It doesn't need to explain how you got from one scene to the next, so the dream feels compressed. Some researchers have tried to measure time in dreams. They used people trained in lucid dreaming, where the person knows they're dreaming and can act within it. These dreamers got cues before sleep, like signals to perform a task in the dream, and then make a movement, like moving their eyes left and right. The researchers then measured the time from the cue to the eye movement. In many cases, dream time lined up with real time, but not always. Sometimes it ran longer, sometimes shorter. This shows that dream time isn't fixed. It depends on how the brain builds the experience. When you're awake, time feels tied to the clock. When we're dreaming, it feels tied to the story. Children experience time more vividly because much of what they see and do is new. When something feels new, the brain pays closer attention. It works harder to process what's happening. That effort stretches the moment. The more attention something gets, the longer it seems to last. This is why a school day in kindergarten feels longer than a workday later in life. It's not just perception, it's the brain laying down fresh memories. Think about a child walking into a zoo for the first time. They don't just see animals, they notice how the lion moves, the way the giraffe chews, the smells in the air, the sounds around them. Their brain records all of it. These new details slow time down. The same trip for an adult might fly by. Adults have seen many zoos. The brain already knows how a lion walks. It stores that as a shortcut. Less new input means less to process, so time feels shorter. Routine speeds time up. When days blur together, they feel shorter in memory. A child's life has fewer routines. They jump from finger painting to learning numbers to building blocks. Their world stays in motion. The more varied the activities, the more markers the brain creates. These markers act like flags in memory. The more flags, the longer the day feels. You might notice this effect during a vacation. A trip to a new city full of new sights and sounds often feels long. Even if it's just a weekend, that's because your brain is busy again. It pays attention the way it did when you were young. The hotel room layout, the street names, the local food, all of it demands notice. Children live in that state more often. They're still learning what most adults already know. The first time tying a shoe or riding a bike sticks in the mind. These moments stretch time. Even waiting feels longer because patience hasn't yet become automatic. 5 minutes before dinner can feel like forever when you don't have a strong sense of how long 5 minutes is. That's not a flaw in childhood. It's part of how learning works. New input builds understanding. It also slows time, not in the clock's hands, but in the mind's sense of the day. Meditation can distort your sense of time. You might sit for 10 minutes and feel like an hour passed. Or you could meditate for half an hour and think only 5 minutes went by. This effect isn't just in your head. It happens because meditation changes how your brain processes time. When you meditate, you usually focus on one thing. This might be your breath, a word, or the sensation of your body sitting still. You tune out distractions. Your brain stops tracking external cues like movement or sound. These cues help your mind build a timeline. Without them, your sense of passing time becomes less accurate. Let's say you sit in a quiet room with your eyes closed. You focus on your breath, going in and out. No phone, no talking, no clock ticking. After a while, your mind stops checking how long you've been sitting. You're not thinking about lunch or your next meeting. Time loses shape. It stretches or shrinks depending on your mental state. The brain's internal clock depends on something called the default mode network. This network lights up when your mind wanders. It helps you think about the past and the future. But meditation turns that network down. You stop thinking about what happened yesterday or what you'll do tomorrow. You stay in the present moment, and in that space, time doesn't follow normal rules. You might also notice changes depending on how experienced you are. Beginners often feel time drags. Sitting still with nothing to do can feel long. But with practice, you start to sink into the experience. You may go deep into a meditative state and lose track of time altogether. It's not sleep, but it can feel like a blank space where time doesn't matter. This effect isn't limited to formal meditation. Runners, musicians, and artists often feel it too. They call it being in the zone. You concentrate so fully that time fades into the background. Meditation trains your mind to enter that zone on purpose. So the next time you feel time slip away while meditating, know it's not a mistake. It's part of how your mind works when it finally gets quiet. The second is the unit we use to measure time. It's not tied to the motion of the sun or the turning of the earth. Instead, it's based on something much more stable: atoms. More specifically, cesium atoms. Inside every cesium atom, electrons move between energy levels. These movements aren't random. They happen in a very steady rhythm. Scientists call this vibration, though it's not a vibration like the shaking of a phone. It's a shift in the state of the atom that happens at a fixed rate. 1 second is defined as the time it takes for a cesium atom to make 9,192,670 of these transitions. That number isn't rounded, it's exact. Every time we say 1 second, we're talking about that many vibrations. This standard isn't new. In 1967, scientists agreed to use cesium-133 to define the second. Before that, we used the Earth's rotation. But the Earth isn't perfect. Its rotation changes slightly over time. Tides, earthquakes, and even weather can make the Earth slow down or speed up just a little. That's not useful when you need exact time. Cesium, on the other hand, stays constant. You can put a cesium atom in a lab, and it will give you the same number of transitions day after day, year after year. This makes it a good foundation for atomic clocks. These clocks are so accurate that they would only lose 1 second every 100 million years. A lab that keeps an atomic clock has a beam of cesium atoms. These atoms go through a magnetic field and are hit with microwaves tuned to the exact frequency of that transition. If the frequency matches, the atoms flipped states. Sensors detect these flips. When the number of flips is highest, that's how scientists know the frequency is correct. They then lock the clock to that frequency. These atomic clocks set the standard for Coordinated Universal Time, or UTC. GPS systems rely on this. So do internet data centers, financial markets, and power grids. Without a stable and agreed-upon second, none of these would stay in sync. Airplanes wouldn't know where they are. Banks wouldn't timestamp trades correctly. Even simple things like your phone knowing the time would fall apart. The second, defined by cesium, keeps the modern world running on time. A day isn't exactly 24 hours. Most people think of a day as the time it takes Earth to rotate once, but the real picture is more complex. If you measured how long it takes the sun to return to the same spot in the sky, say from noon one day to noon the next, you'd get what's called a solar day. That solar day is, on average, about 24 hours, but it can shift slightly depending on the time of year. Earth's orbit around the sun is not a perfect circle. It's an ellipse, which means our planet moves faster when it's closer to the sun and slower when it's farther away. This uneven speed affects how we see the sun move across the sky. When Earth moves faster in its orbit, the sun appears to take longer to return to the same point overhead. That makes the solar day slightly longer than 24 hours. When Earth moves slower, the solar day is shorter. Also, Earth's axis is tilted. That tilt affects how sunlight falls on different parts of the planet at different times of the year. As the angle changes, so does the apparent speed of the sun across the sky. This also causes the length of a solar day to vary. If you had a very accurate clock and checked solar noon every day, when the sun is highest in the sky, you'd see that it doesn't happen at the same time each day. Some days it's a few seconds earlier. Other days it's later. Over the course of a year, these small changes add up. This is why sundials don't always match your wristwatch. Scientists use a different kind of day to avoid these shifts. A sidereal day measures how long it takes for Earth to complete one full rotation relative to distant stars. This kind of day is about 23 hours, 56 minutes, and 4 seconds. It's more stable, but it doesn't match the sun cycle, so it's not useful for keeping civil time. To make our clocks and calendars line up with the solar day, timekeepers sometimes add leap seconds. These are inserted to adjust for tiny mismatches between atomic time and the solar time we experience. Without these corrections, noon on a clock would slowly drift away from the actual time the sun is overhead. Earth doesn't orbit the sun in exactly 365 days. It actually takes about 365.2422 days. That small fraction of a day adds up over time. If we didn't account for it, our calendars would drift. Eventually, summer would start in October. To prevent that, we add a leap day, February 29th, roughly every 4 years. This extra day helps our calendar stay in sync with Earth's orbit around the sun. The rules for leap years follow a clear formula. Most years that can be divided by 4 are leap years, but there are exceptions. If a year is divisible by 100, it's not a leap year, unless it's also divisible by 400. For example, the year 1900 wasn't a leap year, but the year 2000 was. This rule helps keep the calendar accurate over long periods. Let's say we didn't add leap years. After 4 years, the calendar would be off by nearly 1 day. In 40 years, it would be off by about 10 days. That would shift the seasons slowly but surely. Farmers who rely on seasonal changes would find planting dates harder to predict. Religious holidays tied to the calendar, like Easter, would start to move out of place. Schools, which base their schedules on seasons, would also feel the effects. It would throw off more than just the date. It would shift how we live year to year. This system is part of the Gregorian calendar, introduced in 1582 by Pope Gregory XIII. It replaced the Julian calendar, which added a leap day every 4 years with no exceptions. That calendar drifted by about 11 minutes each year. After centuries, it had shifted the calendar by about 10 days. The Gregorian reform dropped those extra days and added rules for leap years to stop further drift. Leap years aren't just a quirk, they're a fix. Earth doesn't follow human time neatly, so we adjust. A leap year is a practical patch that keeps civil time close to solar time. It's a reminder that our calendar isn't perfect. It's a tool, and like any tool, it needs maintenance to stay useful. Before mechanical clocks existed, people still needed to measure time. One method they used was the candle clock. A candle clock was a tall candle with evenly spaced markings down its side. As the candle burned, the wax melted past each marking. This told people how much time had passed. The idea was simple. Each section of wax took a set amount of time to melt. For example, if a candle had 12 marks and burned for 12 hours, then each mark represented 1 hour. People could glance at the candle and know the time based on how many marks had melted. It didn't matter whether the sun was out or not. Candle clocks worked in total darkness, which made them useful at night or inside buildings without windows. These clocks weren't always precise. If there was a draft, the candle might burn faster. A thicker candle might burn slower. The type of wax also made a difference. Beeswax burned differently than tallow. Still, people found ways to make candle clocks more reliable. They placed them in lanterns to protect the flame. They used standard molds to shape the candles. Over time, users got a sense for how accurate each candle would be. Monks, for instance, used them to schedule prayers throughout the night. In some places, candle clocks helped organize work shifts or nighttime events. Candle clocks had more than one use. Some included nails or small weights at each hour mark. As the wax melted and the nail dropped, it hit a metal plate and made a sound. This sound acted like an alarm or a chime. Imagine being asleep in a monastery and hearing a soft clink as the candle marked the next prayer time. That simple sound told everyone it was time to get up and gather. You could set a candle clock without knowing the exact hour. Just decide how long you wanted it to burn. A merchant might light one at the start of a meeting. When the candle reached a certain point, he knew the time was up. People didn't always need to know the hour and minute. They just needed to track a fixed period. These clocks made sense in a world without electricity or digital displays. They offered a quiet, steady way to track time. The earliest clocks used water. These clocks, called clepsydras, worked by letting water flow from one container to another. The idea was simple. As the water moved, it marked the passage of time. People could watch the water level rise or fall and use that to measure hours. This method was one of the first ways humans tracked time in a steady and predictable way. Imagine a clay pot with a tiny hole at the bottom. You fill the pot with water. As the water drips out, marks along the side of the pot show how much time has passed. Once the water reaches a certain line, a set amount of time is over. This could be an hour or even just a few minutes. In ancient Egypt and Babylon, this kind of tool was common in temples and courts. Priests used clepsydras to time rituals. Judges used them to make sure speakers didn't go over their time in court. Not all clepsydras worked the same way. Some let water flow in, not out. A vessel would sit in a basin of water. As the water rose in the basin, it entered the vessel. When the vessel sank or filled up to a certain mark, time was up. This type of clock worked well at night or on cloudy days when sundials could not be used. Water clocks didn't just track hours. Some complex designs also rang bells or moved figures when the water reached a point. Ancient Chinese inventors made elaborate water-driven mechanisms with gears and floats. These systems needed steady water pressure, so some clocks used tanks to keep flow even. That was tricky because if the water pressure changed, the clock ran too fast or too slow. Despite these limits, clepsydras were among the most reliable timekeepers before mechanical clocks. They didn't need sun or wind. They just needed water. In places where sunlight was unreliable, or when people needed to track time at night, clepsydras were essential. Over time, people built better versions with improved flow control and calibration marks. They remained in use for centuries, showing how a simple tool could solve a constant human need. Imagine a clock so accurate that if it had started ticking at the birth of the universe, it would be off by only a second today. That's the level of precision scientists have reached with the world's most accurate atomic clock. Specifically, it's off by 1 second every 33 billion years. For reference, the universe is only about 13.8 billion years old. This means the clock's margin of error is smaller than the age of everything we know. This clock uses atoms to keep time instead of gears or pendulums. In older mechanical clocks, moving parts create friction and wear, which leads to inaccuracy over time. Even quartz clocks, which vibrate at a stable frequency, drift a bit. Atomic clocks avoid this by measuring the vibrations of atoms, usually cesium or strontium, which oscillate at consistent rates. These atoms act like metronomes, ticking billions of times per second with remarkable regularity. The most precise atomic clocks today use optical lattices, which are grids of laser light that trap atoms. Scientists then hit these atoms with more laser light, tuned to a specific frequency. When the frequency matches the natural vibration of the atom, it triggers a response. That frequency becomes the tick of the clock. Because these vibrations happen so rapidly, hundreds of trillions of times per second, tiny errors are easier to spot and correct. Let's say you used one of these clocks to run the GPS system. Even small timing errors can throw off location data by several meters. That's because GPS relies on signals from multiple satellites, and each satellite carries an atomic clock. If the clock is off by even a billionth of a second, the signal will give you the wrong position. With more accurate clocks, GPS can become precise down to the centimeter. Scientists also use these clocks to study gravity. A clock placed a few centimeters higher will tick slightly faster because it's farther from Earth's gravitational pull. This helps researchers measure elevation changes and gravitational fields in a way no other tool can. Over time, this could lead to better models of Earth's interior or detect small movements in tectonic plates. We once used sundials before mechanical clocks. A sundial works by casting a shadow from a central stick or pointer, called a gnomon, onto a flat surface marked with lines that show the hours. As the sun moves across the sky, the shadow moves, pointing to the current time. This only works when the sun is out. On cloudy days or at night, the sundial is useless. People built different types of sundials for different needs. A vertical sundial could be fixed on the side of a building, useful in cities where space was tight. A horizontal sundial, more common in open spaces, could sit in a courtyard or garden. There were even portable sundials, small enough to carry in a pocket, though they weren't very accurate. Some had to be adjusted for the season. Others needed you to point them in the right direction. But all depended on sunlight and a clear sky. Timekeeping with sundials wasn't precise. The length of an hour could vary throughout the year because the Earth's orbit is slightly oval, not a perfect circle. This causes the sun to move faster or slower at different points in the year, making the sundial run ahead or fall behind. People adjusted for this with something called the equation of time. That was a chart or a rule that told you how many minutes to add or subtract on a given day. In many places, churches or town halls used large sundials to tell time for the community. The bell might ring at noon based on where the shadow landed. Farmers might stop work for lunch when they saw the shadow hit a certain mark. It was a shared time, shaped by nature, not a private number on a wristwatch. But sundials had limits. They didn't work well in far northern or southern areas where daylight changes a lot with the seasons. And they couldn't be used inside, underground, or at sea. For people on ships, tracking time by the sun was hard unless they had the right instruments. That's part of why mechanical clocks mattered so much. But before they came along, sundials gave people a simple, solid way to mark the day. Time zones are a human invention. They didn't come from nature. We made them to solve a problem. Before time zones, people used local solar time. That means noon was when the sun was highest in the sky. This worked fine when people didn't travel far or fast. But as trains and telegraphs connected cities, keeping local time became messy. Imagine a train leaving one city at 11 a.m. and arriving in another at 11 a.m., even though the trip took 2 hours. That's what happened before time zones. Every town had its own clock, set to its own version of noon. When trains and communication crossed regions, all those different times made things confusing and dangerous. Train crashes happened because schedules didn't match. People missed messages or appointments. No one could agree on what time it really was. In 1884, a group met in Washington, D.C. to fix this. They divided the world into 24 time zones, each one covering 15 degrees of longitude. The starting point was Greenwich, England, known as the prime meridian. From there, each zone added or subtracted an hour. That's how we got the system we use today. But even this system isn't perfect. Countries adjust time zones for their own reasons. India uses a half-hour offset. China spans 5 natural time zones but uses only one official time, Beijing time. Some places use daylight saving time, which shifts the clock forward in spring and back in fall. Others don't. So even though the idea of time zones is global, how we use them is not. Think of it like drawing lines on a map. The Earth doesn't have borders or time zones by itself. We draw those lines to make things easier to manage. Time zones are the same. We shape them to fit our needs. They help planes land on time and meetings happen when they should. But they're not laws of nature. They're agreements. If the world agreed to stop using time zones tomorrow and switch to one global time, the sun would still rise and set as usual. Clocks would just show different numbers than we're used to. The sun doesn't care what time you think it is. The International Date Line helps the world keep time straight. It's an imaginary line that runs from the North Pole to the South Pole, mostly along the 180-degree line of longitude. When you cross it, the date changes. If you go west across the line, you add a day. If you go east, you subtract a day. This might sound strange at first, but it keeps time zones from getting out of sync as you move around the globe. Imagine flying from California to Japan. As you travel west, you cross time zones and set your watch forward. When you finally cross the International Date Line, it becomes the next calendar day. For example, if it's Monday in California, it becomes Tuesday in Japan. Without the dateline, some places would be a full day off from their neighbors, and the system of global time would break down. Now think about a ship sailing east from Japan to California. As it crosses time zones, the crew sets their clocks back. When they cross the dateline, they go back a full day. If it was Friday in Japan, it becomes Thursday again in California. This doesn't mean time itself is changing. It's just a way to make sure the calendar stays consistent with the rotation of the Earth. The international dateline doesn't follow a straight line. It zigzags in places to keep countries and islands in the same time zone. For example, Kiribati, a group of islands in the Pacific, decided to move the dateline around its territory in 1995. They did this so all parts of the country would share the same date. Before that, the islands had different days depending on their location. Time zones depend on longitude, and there are 24 hours in a day. So the world is divided into 24 time zones, each one about 15 degrees of longitude wide. But countries and regions often adjust their time zones for practical reasons. The international dateline makes sure that despite these local changes, the whole world agrees on what day it is. That helps planes land on time. Global businesses coordinate meetings, and people around the world communicate without confusion. Coordinated Universal Time, or UTC, is the primary time standard by which the world regulates clocks and time. It does not change with the seasons, unlike daylight saving time. Instead, it stays the same all year. Most time zones around the world are based on UTC, with local adjustments made by adding or subtracting a set number of hours. For example, New York is 5 hours behind UTC during Standard Time and 4 hours behind during Daylight Saving Time. UTC replaced Greenwich Mean Time, or GMT, as the global standard. While people still use the term GMT informally, UTC is more precise. UTC is based on atomic time. Atomic clocks use the vibrations of atoms, usually cesium, to keep time with extreme accuracy. This accuracy is necessary for systems that rely on precise timekeeping, like GPS, stock exchanges, and telecommunications networks. Every second in UTC is measured with great care. When small differences build up between atomic time and the Earth's rotation, a leap second is added to UTC. This keeps UTC in sync with the planet's rotation. Leap seconds are rare. They happen only when the difference gets close to 0.9 seconds. The last one was added in 2016. Airlines use UTC to avoid confusion when flying between time zones. For example, a flight from London to Tokyo might depart at 12 o'clock UTC and arrive at 0 o'clock UTC the next day. This avoids misunderstandings from local time changes. Military forces also use UTC. It gives them a single, clear time reference no matter where they are in the world. Computer systems use UTC to store time data in a consistent way. A server in California and another in Tokyo can use UTC to coordinate without errors from local time zones. Programmers often log events in UTC and then convert them to local time only when needed for display. In everyday life, most people don't think about UTC, but it works in the background. When your smartphone adjusts the clock automatically, it uses UTC as a reference. The network time servers send UTC time to your device, which then applies your local offset. This makes sure your clock stays correct even when you travel or during daylight saving changes. UTC acts as the anchor point for global timekeeping. It ensures everyone speaks the same time language, even when they are far apart. Circadian rhythms follow a 24-hour cycle and help control when we sleep, wake up, eat, and perform daily tasks. These rhythms are part of the body's internal clock. They exist in nearly every living thing, from humans to animals to plants. The cycle does not rely on the clock on the wall, but instead on biological signals tied to light, temperature, and hormones. In people, the circadian rhythm centers around a part of the brain called the suprachiasmatic nucleus, or SCN. This area sits in the hypothalamus and gets direct signals from the eyes. When light hits the retina, it sends information to the SCN. This tells the body it is daytime. The SCN then sends messages to other parts of the brain and body to keep all systems in sync. Melatonin is one of the hormones controlled by the circadian rhythm. When it gets dark, the SCN signals the pineal gland to release melatonin. This helps us fall asleep. When it's light again, melatonin production stops. If this rhythm gets disrupted by travel, shift work, or too much screen time late at night, sleep problems may follow. A person might feel tired during the day and wide awake at night. Over time, this can cause health issues like poor focus, low energy, and even problems with blood sugar or mood. Imagine someone who flies from New York to London. The time zone changes by 5 hours. Their body clock stays set to New York time for a while. So they feel sleepy when it's morning in London and awake when it's bedtime. It usually takes a few days for the circadian rhythm to adjust. This is jet lag. The same happens more subtly when someone stays up late every weekend and then tries to go to bed early on Sunday night to get ready for Monday. Even things like mealtimes, exercise, and social activity affect this rhythm. If a person eats late at night, their body may release insulin at the wrong time, throwing off blood sugar patterns. Someone who exercises at the same time each day helps reinforce their rhythm, making it easier to wake up and fall asleep at regular times. Regularity is key. The more consistent a person's habits, the smoother the rhythm runs. Some people think blind people can't keep regular sleep cycles because they can't see light. But many blind people do keep a circadian rhythm. This rhythm is the body's natural clock. It tells us when to wake up, eat, and sleep. It runs on a 24-hour loop, much like the day and night cycle. Light is the biggest cue for this clock. In people who can see, light enters the eye and hits cells in the retina. These cells send signals to the brain, to a part called the suprachiasmatic nucleus. That area controls the body clock. It helps tell the body when it's day or night. But here's the key point. This part doesn't need normal vision to work. Some blind people still have light-sensitive cells in their eyes, even if they can't see images or shapes. These cells don't help with sight. They only detect brightness. That's often enough to keep the body clock in check. Let's say a man lost his vision in an accident. He can't see anything, no colors, no shapes. But his eyes still have those light-sensitive cells. Even though he can't see, his brain still gets the message that the sun is up. That's how he still wakes up at the same time each day without an alarm. Other blind people might not have any light sensitivity. Their eyes may be damaged or removed. In those cases, the body clock often drifts. Without light cues, their rhythm might run a little long. They might start waking up later and later each day. Doctors call this non-24-hour sleep-wake disorder. It means the internal clock isn't syncing with the 24-hour day. People with this problem might feel tired during the day and wide awake at night. Still, even for those without light perception, there are tools. Doctors sometimes use melatonin or light therapy boxes with special timing. These can help train the body to stick to a rhythm. Schedules also matter. Going to bed and waking up at the same time every day can teach the body when it's time to sleep, even without light. So while sight helps keep the body clock in sync, it's not the only way. The brain uses what it can get. Many blind people, with or without light perception, find ways to keep a steady rhythm. Animals also perceive time, though differently. Their brains measure time in a way that doesn't rely on clocks or calendars. Instead, they rely on rhythms in their bodies, patterns in the environment, and learned routines. A dog may not know what 3 p.m. means, but it can learn that the mail carrier comes around the same time each day. Over time, the dog begins to anticipate this visit. It may start waiting by the window or barking a few minutes before the truck pulls up. The dog isn't counting minutes. Its body is picking up on a cycle. This might involve internal signals like hunger, light levels outside, or even human behavior, like when you turn off the TV or get up from the couch. Researchers have found that different species track time at different speeds. Smaller animals, like flies or hummingbirds, see the world in faster frames. Their brains process visual information more quickly. So their experience of time stretches out compared to ours. This helps them react fast to threats or navigate complex spaces at high speeds. If you wave your hand near a fly, it often escapes before your motion is halfway done. That's because the fly is registering your movement more quickly than you are. On the other hand, larger animals with slower metabolisms like elephants or tortoises perceive changes more slowly. Their sense of time runs at a slower pace. This may explain why they move more deliberately and appear calmer. Their internal clocks aren't rushing them. A second for them may feel more drawn out than it does to us. Memory also shapes how animals feel time. If something unpleasant happened during a walk near a certain street, a dog might resist going that way again, even weeks later. It may not remember the exact day it happened, but it remembers the experience. This kind of episodic memory lets animals build a rough sense of the past and future without needing language. So while animals don't track time like we do, they still respond to its flow. They notice regularities. They anticipate events. Their world is full of cues and rhythms that help them find food, avoid danger, and live in sync with their surroundings. Their sense of time, though different, works just as well in their lives as ours does in ours. Sleep plays a key role in resetting the body's internal clocks. These clocks, known as circadian rhythms, control daily cycles like when we feel sleepy, when we wake up, and when we get hungry. They also guide changes in body temperature, hormone levels, and other important functions. These rhythms follow a rough 24-hour cycle, but they don't run perfectly on their own. They need regular cues to stay on track, and sleep is one of the strongest of those cues. Imagine someone who stays up all night and sleeps during the day for several days. After a while, their body starts to expect sleep at sunrise and wakefulness at sunset. But if that person suddenly starts sleeping at night again, their internal clock doesn't adjust right away. It gets thrown off. That's where sleep plays a corrective role. Going back to a consistent sleep schedule helps pull the clock back in line. The brain takes cues from the timing and length of sleep. And over time, the internal clock resyncs with the outside world. This timing system is based in a part of the brain called the suprachiasmatic nucleus. It responds to light, especially daylight, but it also pays attention to behavior, like sleep and wake times. When we go to sleep and wake up at regular hours, the brain sends out signals that reset this internal clock each day. If sleep is irregular, those signals become unclear. The brain then struggles to keep everything in sync. For example, someone who works rotating shifts may sleep during the day for a week and at night the next. Their body has a hard time adjusting. They might feel tired, get headaches, or find it hard to focus. Even if they sleep the same number of hours, the shifting schedule confuses their internal clock. But when that person returns to a steady pattern of sleep and wake times, the body starts to readjust. Hormone cycles improve. Body temperature patterns return to normal. Appetite stabilizes. Sleep itself acts like a reset button. That's why sleep isn't just about getting rest. It's a tool the brain uses to keep time straight. Without regular sleep, our systems lose rhythm. With it, they find their beat again. Animals also perceive time, though differently. Their brains measure time in a way that doesn't rely on clocks or calendars. Instead, they rely on rhythms in their bodies, patterns in the environment, and learned routines. A dog may not know what 3 p.m. means, but it can learn that the mail carrier comes around the same time each day. Over time, the dog begins to anticipate this visit. It may start waiting by the window or barking a few minutes before the truck pulls up. The dog isn't counting minutes. Its body is picking up on a cycle. This might involve internal signals like hunger, light levels outside, or even human behavior, like when you turn off the TV or get up from the couch. Researchers have found that different species track time at different speeds. Smaller animals, like flies or hummingbirds, see the world in faster frames. Their brains process visual information more quickly, so their experience of time stretches out compared to ours. This helps them react fast to threats or navigate complex spaces at high speeds. If you wave your hand near a fly, it often escapes before your motion is halfway done. That's because the fly is registering your movement more quickly than you are. On the other hand, larger animals with slower metabolisms, like elephants or tortoises, perceive changes more slowly. Their sense of time runs at a slower pace. This may explain why they move more deliberately and appear calmer. Their internal clocks aren't rushing them. A second for them may feel more drawn out than it does to us. Memory also shapes how animals feel time. If something unpleasant happened during a walk near a certain street, a dog might resist going that way again, even weeks later. It may not remember the exact day it happened, but it remembers the experience. This kind of episodic memory lets animals build a rough sense of the past and future without needing language. So while animals don't track time like we do, they still respond to its flow. They notice regularities. They anticipate events. Their world is full of cues and rhythms that help them find food, avoid danger, and live in sync with their surroundings. Their sense of time, though different, works just as well in their lives as ours does in ours. Waiting without distraction makes time feel longer. It's a feeling most people know well. Think about standing in a slow-moving line. You check your phone, but maybe the battery is low or the signal is gone. There's nothing to do except wait. You look around, maybe shuffle your feet, and check the time. Only a minute has passed. Without something to occupy your mind, each second stretches out. The brain measures time based on what it experiences. When you're distracted or busy, your attention jumps from one task to the next. You aren't focused on time itself. You're thinking about what you're doing. But when you remove that stimulation, time becomes the only thing you notice. This is why 10 minutes in a doctor's waiting room, without a phone or magazine, can feel longer than a full hour spent working on a tight deadline. This effect shows up in everyday places. Waiting at a red light feels longer when you aren't listening to music. Riding in an elevator feels slower when you're staring at the numbers and not checking your phone. Even microwaving food can feel endless when you just stand and stare at the clock. People aren't good at tracking time without something to break it up. That's why waiting feels more tolerable when there's background noise, conversation, or movement. Airports add TVs and announcements. Restaurants give out buzzers or seat you near a window. These are small things, but they help your mind attach attached to something besides time itself. Distraction changes how you process time. Without it, your focus tightens. You become more aware of how long things take. Even short delays seem bigger. In some cases, this can make people anxious or impatient. In others, it can feel meditative, like when you're sitting quietly in nature and notice every sound and shift in the air. The difference depends on how you feel about being still. Try riding a bus without headphones, or sit in a cafe without your phone. Time slows down. That change in pace can feel refreshing or frustrating, depending on your mindset. But either way, it shows how much attention shapes your sense of time. Depression can change the way you experience time. When you're depressed, a minute can feel like an hour. Days can drag on, and the future can feel too far away or not real at all. This isn't just a feeling. Research shows that depression can actually distort your perception of time. Someone who's depressed might describe their day as crawling. They might say that they're stuck in slow motion or that time has stopped. This isn't because they're paying too much attention to time. In fact, it's often the opposite. They're caught in a state where time seems disconnected from their usual experience. Imagine someone sitting on the couch for hours. They don't get up, not because they don't want to, but because it feels like there's no point. When they check the clock, they're surprised. Only an hour passed, but it felt like a whole day. This makes it harder to plan or imagine the future. Everything seems out of reach. That job interview next week, it feels like it will never come. Finishing a task tomorrow, it might as well be next year. This time distortion links to how depression affects the brain. Certain parts of the brain help track time, including the insula and the prefrontal cortex. These areas also process mood, attention, and memory. When someone is depressed, activity in these parts often slows down or becomes disrupted. This may explain why time feels strange, too slow, or even stuck. In clinical settings, time perception can also show up in how people describe their past and future. Depressed patients often focus on past regrets and see the future as bleak or empty. This perspective makes the present feel heavier and longer. For example, if someone sees no hope in their career, even a 5-minute task might feel like a burden. That heaviness stretches time. They're not just bored or distracted. Their brain processes time in a different way. Not everyone with depression notices this effect, but for many, it's a daily experience. It adds to the fatigue. It makes routines harder to keep. It even affects how well someone follows treatment, because the rewards of getting better seem too far away to matter. When you're deeply focused, time feels like it slips away. You sit down to solve a problem, write an email, or read a report, and before you know it, an hour has passed. But that same hour drags when you're distracted or bored. You glance at the clock every few minutes. You check your phone. You feel restless. This difference in how we experience time has less to do with clocks and more to do with how our brains pay attention. Focus pulls us into the task. Our thoughts don't wander. We don't split our attention between tabs or conversations or background noise. Instead, we engage with what's in front of us. Our brain filters out anything that isn't useful in the moment. In that state, we don't track time as we usually do. We stop noticing the passing seconds and minutes. That's why the hours seem to shrink. Consider how a programmer might feel when debugging a complex system. They may start the day with a vague sense of what's broken, but once they dive into the logs, run tests, and follow the thread, time compresses. Their focus is full. The work is hard, but the mind is steady. There are no gaps for distraction. At some point, they look up and realize it's well past lunch. The same thing happens to a surgeon during a procedure or a writer in the middle of a draft. Their sense of time takes a back seat. Only the task remains. On the other hand, when you're stuck in a meeting where nothing applies to your work, every minute crawls. Your mind jumps around. You think about what you'll do afterward. You check your notes, but your attention isn't really on them. You count the time because you aren't using it. That lack of engagement stretches time out. This is why focus time is so valuable. It doesn't just help us do better work, it also changes how we live through our day. Hours used with purpose don't feel like they're taken from us. They pass without strain. You don't have to force yourself through them, and afterward, you can often recall them clearly. You remember the problems you solved, not the time you spent. You're in a car, swerving to miss a truck. In the moment, everything seems to slow down. You notice the angle of the truck's wheels, the way your fingers grip the steering wheel, even the look on the face of the driver coming toward you. It all happens in just a few seconds. But later, when you think back, it feels like minutes. This isn't just a trick of memory. It's how your brain handles emotionally intense moments. When you face danger or a strong emotional reaction, your brain releases stress hormones like adrenaline. These chemicals shift your body and mind into a high alert state. Your attention sharpens and your senses heighten. You notice more details. You process information faster. This burst of activity makes the moment feel richer, denser. Your brain stores more data per second than it normally would. That's part of why these events feel longer in hindsight. Picture someone at the edge of a cliff, peering down. Their heartbeat jumps. Their hands start to sweat. They take in everything: the wind on their face, the sound of rocks below, even the feeling of their shoes on the gravel. The brain, anticipating danger, starts to over-record. Time doesn't slow down in reality. The clock ticks the same. But since your brain is working overtime, you experience more in the same stretch of time. Later, that rush of detail makes the event seem to stretch out when you remember it. This also happens in emotional situations that aren't dangerous. Think about a breakup, the moment someone tells you they're leaving. Words slow, faces freeze. It's not that people speak slower, it's that your attention locks in. You remember the exact tone of their voice, where you were sitting, even the pause between sentences. Again, your brain takes in more than usual because it senses the weight of the moment. It's not magic. It's the brain reacting to stress and emotion. The more intense the moment, the more the brain focuses. The more it focuses, the more it records. The more it records, the longer the moment feels when you look back on it. You sit at your desk and check the time. It's 2 p.m. You're waiting for a package, something you've wanted for weeks. You try to focus on work, but minutes feel like hours. You check your phone. Still nothing. The time between glances grows shorter. Each check leaves you a little more restless. You tell yourself to stop, but your mind circles back. It's not the wait that's hard, it's the anticipation. And that anticipation changes how you feel time. Anticipation doesn't only apply to packages. It happens before job interviews, vacations, doctor visits, birthdays, and big tests. It changes your internal clock. When you expect something, you measure every moment against that event. Instead of experiencing time as a stream, you break it into units. How long until this happens? how much time has passed. You no longer move with time, you monitor it. Think about sitting in traffic on your way to a first date. You notice every red light. The driver in front of you seems to brake more than usual. You can't stop glancing at the clock. 10 minutes stretch like 30. You know you're not moving slower, but your brain processes each second more sharply. Time feels heavier. The reverse also happens. When you're deep in something, time slips past you. You look up and realize hours are gone. That happens because your attention stays with the task, not the clock. Anticipation pulls that attention forward. You're not here. You're waiting to be somewhere else. This isn't about impatience. Anticipation carries weight because it often ties to emotion. If you dread the dentist, the days before the appointment drag. If you crave a concert, the same dragging happens. Your body stays in place, but your mind leans toward the future. That lean warps time. It also explains why waiting rooms feel longer than they are. You sit in a space with nothing to do, thinking about what comes next. You may only wait 15 minutes, but the absence of distraction makes that time swell. You feel each tick of the second hand. Your anticipation strips away flow and leaves you counting. Perception of time isn't fixed. It shifts with focus, expectation, and feeling. Anticipation changes not only how you see the future, but how you experience the present. The grandfather paradox questions what would happen if you traveled back in time and killed your grandfather before he had children. If you did that, your parent would never be born, and neither would you. But if you were never born, how could you go back and kill your grandfather? This creates a loop that seems impossible to resolve. It's a common way to explain the problems with changing the past. This paradox shows up a lot in science fiction. A time traveler might go back to stop a war or save someone's life. But once they do that, the reason they traveled in the first place no longer exists. That creates a contradiction. If your actions in the past stop your need to go back, then how did you end up there in the first place? Some people try to solve this by saying the past can't be changed. In that view, even if you go back in time, you're part of what already happened. Let's say you travel back and try to kill your grandfather. Maybe your gun jams, or you miss, or someone stops you. Either way, something stops the act. You don't succeed because you couldn't have. Your presence in the past was always part of the timeline, and it never changed anything. This view treats time as fixed and unchangeable. Others suggest that changing the past creates a new timeline. In this version, you kill your grandfather, and that creates a new reality where you're never born. But the original timeline still exists, and you're still alive in it. It's like you branched off into a different version of the world. This idea allows for change, but only within separate timelines. It avoids the paradox by saying both outcomes can be true in different branches. Still, not everyone agrees that time works this way. We don't have proof that time travel is possible, even if we could go back. We don't know what rules would apply. The grandfather paradox doesn't just test logic, it questions how cause and effect work. If the past can be changed, then our whole understanding of time and history needs a rewrite. Wormholes are a theoretical way to travel through time. A wormhole is a shortcut through space and time. Instead of traveling from one point to another in a straight line, you fold space like a piece of paper and pass through the fold. Scientists call this a solution to Einstein's equations of general relativity. These equations describe how gravity shapes space and time. Wormholes are not proven to exist, but they are allowed in theory. Imagine space as a flat sheet. If you draw two dots far apart and then bend the sheet until the dots touch, you create a shortcut. This is the basic idea of a wormhole. If such a tunnel existed, You could enter at one end and come out at the other without moving through the space in between. Now, if the two ends of the wormhole are in different times, not just different places, then traveling through it would let you move through time. To use a wormhole for time travel, you need to make one end move relative to the other. For example, you place one end on a spaceship and fly it around at near the speed of light. Due to time dilation, a real effect where moving clocks tick more slowly, less time passes for the moving end. When you bring the two ends back together, one of them is now in the past relative to the other. Step through and you step into the past. This setup has problems. The biggest one is stability. A natural wormhole would likely collapse before anything could pass through it. To keep it open, you need exotic matter. This kind of matter has negative energy density, something we do not see in large amounts. Quantum theory suggests it might exist, but we have never observed it directly. Even if we could find or create exotic matter, we don't know how to use it to build a wormhole. There's also the risk of paradox. If you travel into the past, you might change something. Say you went back and stopped your grandfather from meeting your grandmother. Then you might never be born. If you're not born, how did you go back? This is called the grandfather paradox. Some physicists think the universe avoids paradoxes by preventing changes to the past. Others suggest multiple timelines. If you go back and change something, you split into a new timeline. Your original timeline remains unchanged. So far, wormholes remain a thought experiment. They help physicists explore the limits of what we know about space, time, and gravity. They show what might be possible, even if it's far beyond our current reach. In the twin paradox, one twin travels through space at a high speed while the other stays on Earth. When the traveling twin returns, they are younger than the one who stayed behind. This result might seem strange, but it comes straight from Einstein's theory of special relativity. Time does not move at the same rate for everyone. When someone moves very fast, close to the speed of light, time slows down for them compared to someone who stays still. This effect is called time dilation. It's not just a theory. Scientists have tested it using atomic clocks on fast-moving jets and satellites. These clocks tick slightly slower than identical ones on the ground. Now think about the two twins. Imagine the traveling twin leaves Earth in a spaceship that flies near the speed of light. The ship travels far away, then turns around and comes back. To the twin on the ship, the trip might feel like a few years, but to the twin on Earth, much more time has passed. When the spacefaring twin steps out of the ship, they look younger. The twin on Earth looks older. Some people ask, doesn't each twin see the other one moving? Shouldn't both think the other age slower? That's a good question. The key point is that the situation isn't the same for both. The twin on the ship turns around. That means they change direction and speed. This change breaks the symmetry. The Earth-bound twin never changes their motion. They stay in one steady frame. The twin on the ship does not. This difference makes one twin truly younger, not just from a certain point of view. Picture this. You are the traveling twin. You blast off and head to a star 10 light years away. You travel so fast that the trip takes only 5 years from your view. You turn around and come back. 10 years have passed for you. But when you land, your sibling tells you that 20 years have gone by on Earth. You've aged 10 years. They've aged 20. You didn't dream it. You really did spend less time aging. The twin paradox isn't a trick. It's a real effect of how time works when you move fast. It shows that time is not fixed. It can stretch and shrink, depending on how you move through space. Faster than light travel would break one of the most basic rules of how we understand time. That rule is causality. In simple terms, causality means that a cause must come before its effect. For example, if you flip a light switch, the light turns on afterward. The cause, the flip, comes before the effect, the light turning on. Faster than light travel flips that order around in some situations. Imagine a spaceship that can travel faster than light. Let's say it leaves Earth and reaches a star system 4 light years away. With faster than light speed, the ship arrives there in less than 4 years. Now imagine someone at that star system sends a message back to Earth, also using faster than light travel. Because of how time and space interact at these speeds, the message might arrive back on Earth before the spaceship even left. That's not just strange, it creates a paradox. It's like getting a birthday card before your friend even writes it. Physics has ways to track how events happen in time, even when people are moving at different speeds or in different places. This tracking comes from Einstein's theory of relativity. It uses what's called spacetime intervals to sort out which events can influence each other. If something moves faster than light, these intervals break down. One person might see the spaceship leave first and arrive second. Someone else, moving at a different speed, might see the ship arrive before it ever left. Both views would be valid under the math, but they can't both be true in real life. This matters because it opens the door to things like the grandfather paradox. That's a thought experiment where someone travels back in time and stops their grandfather from meeting their grandmother. If they succeed, they would never be born and couldn't have traveled back in time in the first place. Causality stops these problems from happening by making sure time only moves one way, forward. Faster than light travel lets you loop around that forward-only rule. Once that happens, all bets are off. You could send messages to the past. You could change events before they happen. That's why physicists believe that if faster than light travel is ever possible, it would need to come with something that protects causality. But so far, no one has found a way to do that. Time loops show up often in science fiction because they let characters relive the same stretch of time over and over. These loops can be short, like a single day, or long, like a mission that repeats every time it fails. Writers use this device to explore cause and effect, choice, and what happens when someone has too much time on their hands. In most stories, one person knows they're stuck in a loop. Everyone else resets when time starts over. That creates tension. Imagine a soldier waking up every morning knowing the battle will go wrong again. Or think of someone trying to stop a disaster, failing and trying again with a little more information each time. With each loop, they learn, they change, but the world around them stays the same until they figure out how to break the loop. A clear example is the film Edge of Tomorrow. The lead character dies during combat and wakes up at the start of the same day. At first, he panics. Later, he trains, makes plans, and gathers knowledge. The movie shows how repetition can be a tool. Every loop becomes a lesson. Time becomes something to master, not just pass through. In another story, Groundhog Day, the loop isn't about battle, it's about personal growth. The main character repeats the same day in a small town. At first, he uses the loop for selfish gain, but he gets bored, then frustrated, then finally turns to helping others. The loop forces him to change in a way normal time never would. In both stories, time loops trap characters in a cycle, but that trap becomes a tool and then a test. Writers also use loops to explore the limits of memory and emotion. Say someone watches a friend die 100 times, always trying to save them, but failing. The loops become a burden. The stakes don't change, but the toll on the character gets heavier. In these cases, time loops are not just a way to stretch time, they are a way to stretch the mind. Science fiction likes time loops because they take something familiar, cause and effect, and turn it upside down. The same moment repeats, but meaning changes each time. That keeps the story grounded, even while the structure becomes strange. Some scientists think the universe might not have a true beginning or end. Instead, it might loop. This idea says time itself runs in a cycle. The universe expands, slows down, collapses, and then begins again. Over and over. It's like breathing. Inhale, exhale, repeat. This isn't a new thought. Ancient traditions spoke about time as a wheel. Now, physics circles back to a similar view. Some models in cosmology support the idea. They show how the universe could reset itself without needing a big bang from nothing. Here's how it could work. Right now, we see the universe expanding. Galaxies move away from each other. This started about 13.8 billion years ago after the Big Bang. The expansion might keep going. Or, if there's enough matter or force to slow it down, the universe could stop stretching. Gravity could take over. Everything would begin to fall back inward. If that happens, the universe could collapse into a dense state again. This collapse is sometimes called the Big Crunch. After the crunch, conditions could spark another Big Bang. Then the cycle starts again. Expand, collapse, reset. In some versions of the theory, time doesn't stop during the collapse. It bends or turns. So when the universe reaches its tightest point, time loops back. The new universe may even be the same as the last. Or small changes could mean each cycle has differences. Galaxies form in new ways. Stars take on new paths. Still, the laws of physics remain the same. This looping view raises questions. Do we live in the first cycle or the thousandth? Would anything from a past cycle remain? Could particles or forces carry over? Some think dark energy or the shape of space might hold a memory. But right now, we don't know. To test these ideas, scientists study cosmic background radiation, the faint light left over from the Big Bang. If past cycles left a mark, it might show up in that light. So far, we haven't found clear proof, but the search goes on. In labs and on paper, physicists work through equations. They try to build models that match what we see in space. These models don't need a start from nothing. Instead, the universe always was, always will be, looping, turning, cycling through time. Time travel to the future is possible. This isn't science fiction. It's a consequence of Einstein's theory of relativity. The idea is simple once you strip it down. Time doesn't move the same for everyone. How fast you move affects how fast you experience time. If you move fast enough, time slows down for you compared to someone standing still. This effect is called time dilation. Let's say you travel on a spaceship that moves close to the speed of light. To people back on Earth, your trip might take years, but to you, it could feel like a few weeks or months. When you come back, more time has passed for everyone else than for you. You've moved into their future. This isn't just theory. We've seen it happen. GPS satellites experience time slightly faster than we do on the ground. Their clocks drift unless we correct them. That's because they're farther from Earth's gravity and they're moving quickly. Both those things cause time to tick differently. We've tested this with high-speed planes too. In the 1970s, scientists flew atomic clocks around the world. When the clocks returned, they showed less time had passed compared to clocks that stayed on the ground. The difference was tiny, but it matched the predictions. The reason for all this comes down to how time and space are linked. When you move through space, you give up some movement through time. It's like a budget. You can't spend fully in both. The faster you go, the less time you experience. So if someone could move fast enough for long enough, they could leap far into the future. Now, traveling at those speeds is hard. It takes enormous energy. Right now, our best spaceships can't get close to light speed, but the physics doesn't say it's impossible. It just says we'd need better technology. You don't need a wormhole or a time machine. You just need to move fast enough or sit near something with strong gravity like a black hole. Gravity slows time too. The closer you are to a massive object, the slower time moves for you. In theory, if you hung near a black hole's edge and then left, you could find yourself far in the future compared to everyone else. Time travel to the future is real. We just need the means to scale it up. Time travel to the past remains speculative. No scientific theory today proves it can happen. People have imagined it for a long time. Stories about time machines show up in books, movies, and television. These ideas are fun, but they are fiction. Real physics does not offer a working method to go back in time. Physicists use Einstein's theory of relativity to explain time. According to it, time is not separate from space. They form what's called spacetime. Objects with mass bend spacetime. This bending affects how time passes. That's why time can run slower near a strong gravity source. It's called time dilation. Astronauts on the International Space Station experience this. They age a tiny bit slower than people on Earth. But this does not let them go back to yesterday. It only changes how fast they move through time. Some scientists have thought about closed time-like curves. These are loops in space-time where an object could, in theory, return to its own past. Wormholes might allow this if they exist. A wormhole is a shortcut through space-time. Think of it as a tunnel with two ends in different times or places. If one end moves in a certain way, the tunnel might link different points in time. The problem is, we don't know if wormholes exist. Even if they do, we don't know how to keep one open or stable. Some theories say it would need a type of matter with negative energy, which we have never observed. There are also issues with paradoxes. Imagine you go back and stop your grandparents from meeting. Then you would never be born. But if you were never born, how could you go back in time? This is called the grandfather paradox. It shows how time travel to the past could cause logical problems. Some theories try to solve this. They suggest that if you change the past, you split off a new timeline. But we have no proof this happens. These ideas are interesting, but they are guesses. No one has ever shown a time traveler from the future or past. No device has moved someone back to a previous point in time. Every test and experiment so far supports the idea that time moves one way, forward. A Tipler cylinder is a theoretical way to travel through time. It comes from general relativity, the branch of physics that deals with how gravity affects space and time. The idea is simple in concept, but hard to build in real life. Imagine a very long, very dense cylinder that spins fast, so fast that it twists the fabric of space-time around it. If the cylinder spins at the right speed, and if it's long enough, it could let something or someone move in a closed loop through time. This loop is called a closed time-like curve. The math behind it checks out, at least on paper. Frank J. Tipler, a physicist, described it in the 1970s. He showed that under certain conditions, a spinning cylinder could cause space-time to bend in such a way that it folds back on itself. That means if you traveled the right path near the cylinder, you could end up where and when you started. To work, the Tipler cylinder needs to be infinitely long or nearly so. If it's too short, the time loop doesn't form. That's a big problem. Nothing in the real world is infinite. Even a super advanced civilization would struggle to make something close. The cylinder also needs to spin at nearly the speed of light, which takes huge amounts of energy. On top of that, the material would have to be extremely dense, far denser than anything we can make now. We're talking about mass on the level of neutron stars, squeezed into a thin, spinning rod. Let's say you manage to build one. Now you fly a ship near the cylinder, just outside its surface. You circle it several times in the right direction, close enough for spacetime to affect your path. If everything works, you loop back in time and arrive before you left. It wouldn't feel like anything special. No sudden jolt or flash of light. You'd just notice the clocks running differently and the outside world out of sync. But the moment you try to make the cylinder finite, the whole effect falls apart. The math stops working, so it stays stuck in the realm of thought experiments. Scientists use it to explore what general relativity allows, not what people can build. The Tipler cylinder gives a glimpse into how strange and flexible space-time can be, even if it never becomes real. Some physicists think time might have more than one dimension. Most people see time as a straight line. It flows from past to present to future. We move along this line in one direction at one speed. This matches our daily experience. But some theories in physics suggest this may not be the full story. In math and physics, we already use more than 3 dimensions to describe the universe. Space has 3: length, width, and height. Time is usually added as a 4th. It helps us describe events and motion. But this 4th dimension is treated differently. It moves in one direction, unlike space, which we can move through in any direction. Some researchers wonder if this one-direction idea is too limited. What if time, like space, had more directions? To think about this, imagine standing at a crossroads. You can walk forward, backward, left, or right. That's how we move through space. If time had 2 dimensions, then we might be able to turn. In time, just like we turn in space, instead of a line, time might be more like a surface. This opens the door to more complex paths. You might move through time in a loop, or drift sideways into another timeline. Some theories in string theory and quantum gravity allow for extra time dimensions. These are not easy to picture. Our brains are trained by everyday life, where time has one direction. But in the math, a second time dimension can make some models work better. For example, having 2 time dimensions can help with certain equations in quantum mechanics. It can also help explain why particles behave the way they do. Of course, no one has seen this second time dimension. It may be hidden, curled up in a tiny space we can't reach. Or it may be that it affects things in ways we don't yet understand. Some scientists have tried to find traces of it in particle collisions. Others look at black holes or the early universe for signs. It's also possible that we will never detect another time dimension. But thinking about it pushes physics forward. It makes us question how we define reality and what limits we accept. Time may seem simple, but it could be much stranger than we think. The cosmic microwave background radiation, or CMB, is a faint glow that fills the universe. It comes from a time when the universe was very young, just about 380,000 years old. At that point, the universe had cooled down enough for atoms to form. Before that, it was too hot for electrons and protons to stick together. Everything was a fog of charged particles, and light couldn't travel far without bouncing off something. But when the universe cooled, atoms formed and light could move freely. That light is what we now see as the CNB. This radiation is everywhere. No matter where we look in the sky, we see it. It's very cold, about 2.7 degrees above absolute zero, but it carries important information. It shows small differences in temperature and density across space. These differences are tiny, just a few parts in 100,000, but they matter a lot. They show the first signs of the structure in the universe, places where galaxies and clusters of galaxies would later form. Scientists measure these small changes with satellites and ground-based telescopes. They look at how the temperature varies from one point in the sky to another. One example is the WMAP satellite, which mapped the whole sky and showed a detailed picture of these changes. Another is the Planck satellite, which provided even sharper images. These measurements help us figure out what the early universe was made of and how it behaved. They support the idea that the universe began with the Big Bang and has been expanding ever since. The CNB also tells us how fast the universe is expanding, how much matter and energy it contains, and whether space is curved or flat. Think of it like an old photograph. The CNB shows what the universe looked like before stars and galaxies existed. It's not a picture in visible light. It's a picture in microwave radiation, which our eyes can't see. But with special instruments, we can read it clearly. It's like tuning a radio to hear a signal that's always been there, just waiting to be found. The Big Bang marks the beginning of measurable time. Before this event, we can't speak about seconds, minutes, or years. Time, as we understand it, did not exist. The Big Bang was not an explosion in space. It was the sudden appearance of space and time itself. All the matter and energy in the universe was packed into a single point, often called a singularity. Then, about 13.8 billion years ago, that point began to expand. With that expansion came the start of time. Imagine a balloon lying flat. You draw dots on it to represent galaxies. As you blow up the balloon, the dots move apart. The dots themselves don't grow. The space between them does. The universe behaves in a similar way. The galaxies are not flying away through space. Space itself is stretching, and the galaxies are carried with it. This expansion started with the Big Bang. Because the universe is expanding, we can measure how fast things are moving apart. Scientists use something called redshift. Light from distant galaxies shifts toward the red end of the spectrum as the space between us and them grows. This gives us clues about how fast the universe is expanding and helps us trace back in time to that first moment. One key idea is cosmic background radiation. This is a faint glow found in every direction. It's the leftover heat from the Big Bang, cooled down over billions of years. We can still detect it with special instruments. Its presence supports the theory that the universe began in a hot, dense state and then expanded. Time started with that first expansion. Before it, there was no before in the way we think of it. Our laws of physics break down at that point. Einstein's theory of general relativity tells us how space and time behave, but it can't describe the moment of the Big Bang itself. That requires quantum gravity, a theory that doesn't fully exist yet. The passage of time since then has been marked by change. Galaxies formed, stars ignited, and planets took shape. Atomic clocks now measure time with incredible precision, but their ticking depends on the physical laws set in motion at the Big Bang. Without that event, even the idea of a clock makes no sense. Most people think of the Big Bang as an explosion in space, like a firecracker going off in the night sky. But the Big Bang was not an explosion in space. It was an expansion of space. This idea alone is strange enough. But it gets even stranger when we ask, what happened before the Big Bang? The short answer is that there may not have been a before. Time itself could have started with the Big Bang. This isn't just a guess. It comes from the way general relativity and quantum theory describe the universe. Think of time as a direction, like up or down. Right now, you can look back in time by studying the universe. You can see galaxies as they were millions or billions of years ago. You can track the expansion of the universe. If you follow that expansion backward, you reach a moment when everything was packed into a very small, very hot space. That's the Big Bang. Keep going even further back and the math breaks down. Space and time shrink to a single point. That point is called a singularity. In everyday life, time feels simple. You wake up, go to work, eat dinner, go to sleep. But in physics, time is not just a background stage where events happen. It's part of the system. Einstein's theory shows that space and time are connected. When something has mass, it bends space and time around it. So time is affected by matter, energy, and gravity. If space and time are linked, and space began with the Big Bang, then time did too. Before the Big Bang, there was no space. And if there was no space, then there was no time either. The clock didn't just read zero, it didn't exist at all. Some theories try to go beyond this. Quantum gravity ideas, like loop quantum cosmology, suggest that the universe may have bounced from a prior state. Imagine a balloon shrinking to a tiny size, then expanding again. In this view, there was something before the Big Bang, but it didn't look or behave like our universe does now. But even those models don't describe time as we know it. What we call before doesn't make sense if time itself wasn't running. It's like asking, what's north of the North Pole? The concept falls apart. Some theories in physics suggest our universe may be just one of many. These other universes, often called the multiverse, could each follow different rules. In some versions of this idea, time itself might work in ways we can't imagine. That doesn't mean clocks run backward or people live forever. It means time could move differently, or even not exist at all, depending on the rules of each universe. In our universe, time moves forward. We see causes come before effects. A glass falls, then it breaks. But in another universe, cause and effect might flip. The break might come before the fall. That would feel strange to us, but if someone lived in that universe, it might seem normal to them. Some theories in quantum mechanics and cosmology allow for such changes. For example, in loop quantum gravity, space and time are not smooth. They are made up of tiny bits, like pixels on a screen. That might mean time ticks forward in chunks, not in a smooth flow. In another type of multiverse theory, called eternal inflation, some regions expand forever. Each new bubble of space could have its own time structure. One bubble might stretch time so slowly that a second there feels like a year here. Another might collapse so fast that time runs out almost as soon as it begins. Imagine you're in a universe where time loops. You wake up, eat breakfast, and go to bed. Then the loop starts again. You live the same day over and over. That's one possible rule for time in a different universe. Or picture a place where everything happens at once. Past, present, and future are not separate. Every moment exists together. No one waits for anything. That world wouldn't need memory or planning. it would have no history or future, just a thick present. Physicists explore these ideas using math and models. We don't have proof of these other universes, but if the multiverse is real, it makes sense that some parts might not follow the time rules we know. We may only understand one version of time. Other versions might work just as well somewhere else. Entropy measures disorder or randomness in a system. Over time, entropy increases. This is a core idea in physics, known as the second law of thermodynamics. It applies not just to machines or ice melting, but to the entire universe. From the Big Bang to today, entropy has kept growing. In the early universe, things were dense and hot. Energy and matter were packed into a small space. Particles collided often, and temperatures were almost even across the cosmos. Still, the universe was in a low entropy state. That might seem strange, since everything was so energetic and full of motion. But what mattered wasn't how hot things were, but how structured and ordered the whole system was. As the universe expanded, matter spread out. Stars formed from clouds of gas. Galaxies spun into shape. These structures look more complex, but they came about because the universe's energy started to flow in more uneven ways. That unevenness allows entropy to increase. Stars burn fuel and release heat, which escapes into space. The heat doesn't come back. It moves outward and spreads thinner. This one-way process adds disorder, increasing entropy. Consider a star like the Sun. It burns hydrogen into helium. That reaction gives off energy. Some of that energy helps life on Earth, but most of it spreads into space. Once used, that energy can't be gathered again in the same form. Over billions of years, stars run out of fuel. They become white dwarfs, neutron stars, or black holes. These end states are more disordered. The usable energy is gone. Entropy has increased. On Earth, we see this process in daily life. A cup of hot coffee cools down. The heat flows into the air. It never gathers itself back into the cup. That's entropy in action. The same logic applies on the largest scale. The universe is cooling. Stars are dying. Black holes evaporate over vast time spans. In every case, order gives way to disorder. Eventually, if the universe keeps expanding, it will reach a state where no usable energy remains. This is called heat death. Everything will be evenly spread out and cold. No more stars, no more light. Entropy will be at its maximum. Nothing more can happen because nothing will have the energy to change. Time and space are not separate. They work together as a single fabric called spacetime. This idea comes from Einstein's theory of relativity. Before that, people thought time moved forward like a ticking clock, the same for everyone. They thought space was just the area around us, empty and fixed. But this isn't how the universe works. Imagine you are sitting on a train. Someone stands still outside the train. To both of you, time seems to pass in the same way. But when the train starts moving very fast, close to the speed of light, something strange happens. Time slows down for you compared to the person standing still. This isn't a trick. It's not about how fast your watch ticks. It's real. If you stayed on the fast-moving train for a year, when you got off, more than a year might have passed for the person who stayed still. This effect is called time dilation. Now picture a heavy object like the Earth. It doesn't just sit in space. It bends space-time around it. Think of a bowling ball on a stretched rubber sheet. The sheet dips under the ball. If you roll a marble near the dip, it moves around the ball. That's what gravity is, a curve in space-time caused by mass. Objects like the moon move around Earth because of this curve, not because Earth pulls on them like a rope. So time and space can't be pulled apart. If you change one, you affect the other. This is why GPS satellites have to adjust their clocks. They move fast and are far from Earth, so time moves differently for them. Without those adjustments, your GPS would give you the wrong location. Spacetime lets us understand black holes too. These are places where mass becomes so dense that spacetime curves in on itself. Nothing, not even light, can escape. The deeper the curve, the stronger the gravity. Near a black hole, time slows down a lot. If you hovered close to one, time would crawl for you, but someone far away would keep aging normally. Understanding spacetime helps us grasp how the universe works, not just stars and planets, but how time passes and how motion feels. It's the stage on which all events in the universe happen, and it shapes every part of our lives. In the early universe, time didn't behave the way we experience it now. Right after the Big Bang, the universe was much denser than it is today. Everything we now see, spread across billions of light years, was packed into a space much smaller than a grain of sand. This extreme density made time move differently. It didn't flow the way it does now because gravity affects time. Einstein's theory of general relativity explains this. It says that the presence of mass and energy bends space and time. When the density of mass and energy is very high, the bending is extreme. Time slows down near massive objects. On Earth, this effect is tiny but real. A clock at sea level ticks more slowly than a clock on top of a mountain. In the early universe, when all matter and energy were crammed into a tiny space, this effect was far more intense. Imagine standing near a black hole. Its gravity is so strong that time slows to a crawl the closer you get to it. From far away, someone might see your movements stretch and slow. The early universe was like that, but everywhere. Where you were, the density was so high that time passed more slowly compared to now. Think about heating a pan of water. At first, the water is calm and slow to move. As you add heat, the molecules gain energy and move faster. In a way, space was like that. As the universe expanded, it cooled and became less dense. With lower density, the grip of gravity on time loosened. Time picked up speed. The cosmic microwave background, a faint glow still visible in the sky, comes from when the universe was about 380,000 years old. But because time moved differently back then, that age doesn't translate neatly to today's experience of time. If you had a clock back then, it would tick slower. From our point of view now, everything in that early period unfolded in slow motion. This is more than theory. Satellites and telescopes measure this stretching of time by looking at light from distant galaxies. The light has been stretched by the expansion of space and by the slowing of time in the past. These two effects, space growing and time shifting, are tied together. You can't talk about one without the other. So when we say the early universe was young, we have to adjust our idea of what that means. Time itself was stretching, changing pace, shaped by the weight of everything packed into one small place. When we look at the stars, we don't see them as they are now. We see them as they were. Light takes time to travel. This means that light from a distant galaxy began its journey long before it reached us. Some of the light we observe today left its source billions of years ago. So, when we look at distant galaxies, we look into the past. The speed of light is fixed. It moves at about 186,000 miles per second in a vacuum. That sounds fast, and it is. But the universe is huge. Even light needs time to cross that space. The nearest star beyond our sun is over 4 light years away. This means its light takes more than 4 years to reach us. If a star is 10 million light years away, we're seeing light that started moving toward us 10 million years ago. It's like watching a message that took a long time to arrive. This delay works like a time machine. Imagine you're in a dark field with a telescope. You point it at a faint object. What you see isn't happening now. It's something that happened when early humans were first using tools or when Earth looked very different. Light carries information. Each photon that arrives at a telescope holds clues about the time and place it came from. We analyze this light to learn about a galaxy's age, its stars, and its movement. Astronomers use tools like spectrometers to break light into parts. These tools help us understand what elements are in a galaxy or star. They also help us measure redshift. Redshift happens when light stretches due to the universe expanding. The more redshift, the farther the galaxy, and the further back in time we are looking. A galaxy with a high redshift shows us what the universe looked like not long after it formed. Think of looking at a birthday photo. It doesn't show you now. It shows a moment frozen in time. Looking at distant galaxies works the same way. We study light to see those frozen moments. The further out we look, the deeper into the universe's history we reach. This isn't guesswork, it's data, captured and decoded, photon by photon. The expansion of the universe changes how we measure time, even if we don't notice it in everyday life. To understand this, imagine the universe like a balloon. As the balloon inflates, the surface stretches. In space, this stretching happens in all directions. When light travels through space, it also gets stretched. This stretching is called redshift. It means the light's wavelength becomes longer and its energy drops. It also means that the time between each wave of light grows longer. That's the key. The time between signals increases. Now picture a galaxy far away. It sends out light. That light takes billions of years to reach us. But because space is expanding while the light travels, the journey becomes longer than you'd expect just from the distance. Time stretches too. If we had a clock in that galaxy ticking once every second, and we watched that clock from Earth, we would see it ticking slower than 1 tick per second. That's not because the clock is broken. It's because the space between us and the galaxy has stretched out while the light was coming our way. This is time dilation caused by cosmic expansion. This time dilation doesn't just affect light. It changes how we measure the age of distant events. A supernova, for example, might seem to fade more slowly than one nearby. The further away something is, the more stretched its signals become by the time they reach us. Scientists take this into account when they study the early universe. They know that if they see a flash of light from 10 billion years ago, the light didn't just travel a fixed distance. The space it moved through was growing the whole time. This is why astronomers talk about look-back time. It helps separate the time light took to reach us from the actual age of the event. The further back we look, the more stretched time becomes. That's not something we feel in daily life, because the expansion doesn't affect local space in the same way. Our clocks and GPS systems work fine because they rely on nearby signals. But when you look at the universe on a large scale, time is not as steady as it seems. The expansion of space pulls on time itself, making the past arrive more slowly than we'd guess by distance alone. Time may end in a big freeze, a big crunch, or a heat death. These are 3 ideas that scientists use to describe how the universe might end. Each one depends on how the universe expands and what happens to matter and energy over a long period of time. The big freeze happens if the universe keeps expanding forever. Right now, galaxies are moving away from each other. If this continues, stars will burn out, galaxies will grow dark, and energy will spread too thin to support life or any activity. Over trillions of years, stars will die off one by one. New stars won't form because gas clouds will become too spread out to clump together. Planets will drift in the dark, cold emptiness. Even black holes will slowly evaporate through a process called Hawking radiation. The universe would grow cold and quiet. Time would still tick forward, but nothing would change. No heat, no light, no activity. Just cold space and dead matter. The Big Crunch is the opposite idea. It could happen if gravity overcomes the expansion. In this case, the expansion would slow down, stop, and then reverse. Galaxies would fall back toward each other. Space would shrink. Temperatures would rise as matter packed tighter. Stars and planets would collide. Black holes would swallow everything. At some point, all matter could collapse into one dense point. Some think this might restart the universe in a new Big Bang, but there's no proof yet that this would happen. Then there's heat death, which is often used to describe the Big Freeze, but it focuses more on energy. All activity in the universe needs a difference in temperature, from hot to cold. Once everything spreads out and reaches the same temperature, no energy will flow. Without flow, there's no work. Machines won't run, stars won't shine, atoms might still exist, but they won't do anything. Over time, even subatomic particles may decay. It's not an explosion or collapse. It's a slow, quiet fade. Each of these endings is based on our current understanding of physics. The exact path depends on dark energy, gravity, and the shape of space itself. We may not see these endings, but they help us understand where the universe might be headed. The ancient Egyptians kept track of time using the moon. They watched the sky every night. They saw that the moon changed shape in a steady cycle. First, it grew from a thin crescent to a full circle. Then it shrank back again. This full cycle took about 29.5 days. That was close to 1 month. Egyptians called this a lunar month. They used these lunar months to build a calendar. 12 lunar months made a year of about 354 days. That's 11 days shorter than a solar year, which is based on the sun and the seasons. Egyptians noticed that this caused a problem. Over time, their calendar drifted. Holidays meant to fall in certain seasons slowly shifted to different times of the year. To fix this, Egyptians later added extra days. They created a civil calendar with 12 months of 30 days each. That made 360 days. Then they added 5 more days at the end of the year. These were feast days. That brought the total to 365 days, which matched the solar year more closely. But at first, their timekeeping came from watching the moon. Each new moon marked the start of a new month. Priests or astronomers likely tracked this from temples. They knew how to watch the horizon and the stars. The first thin crescent after a dark moon told them the new month had begun. This mattered for farming. It helped them decide when to plant or harvest. It also shaped their religious life. Many festivals followed the lunar cycle. Imagine a farmer waiting for the right time to plant wheat. He would watch the moon at night. When the crescent appeared, he would mark the start of a new month. After a certain number of days, he would know it was time to sow seeds. If he missed the sign, the Nile might flood before his crops grew strong. The moon also helped guide temple rituals. Some ceremonies had to happen under a full moon. The priests would plan ahead by counting days from the last new moon. They didn't need machines or clocks. They just needed a clear sky and patience. In this way, the moon shaped daily life. It was the first regular clock people could rely on. The Mayans used one of the most complex calendar systems in the ancient world. They didn't rely on just one calendar. Instead, They used several at the same time, each with its own cycle and purpose. The two most common were the Tzolk'in and the Hab. They worked together like gears in a machine. When one completed a cycle, it moved the other forward. This combination formed a larger cycle called the calendar round. The Tzolk'in had 260 days. It wasn't based on the solar year. Scholars believe it may have tracked the length of a human pregnancy or some kind of ceremonial rhythm. It used 20 day names and 13 numbers, each day name paired with a number. After 260 unique combinations, the cycle restarted. The Hab had 365 days. It was the closest to what we now call a solar year. It had 18 months of 20 days each, plus 5 nameless days at the end. These 5 days were thought to be dangerous or unlucky. People stayed indoors. They avoided big decisions or travel during this period. These two calendars interlocked and repeated every 52 years. That was the calendar round. To track longer spans, the Mayans used the long count. It counted days from a set starting point. That point matched what we call August 11th, 3114 BCE. From there, the long count marked time using a system of units called baktun. Katun, tun, uinal, and kin. A baktun held about 394 years. The Mayan date 13.0.0.0, which once caused rumors about the world ending in 2012, simply marked the end of a full cycle, like turning over the odometer in a car. Mayan priests used these calendars not just to track seasons or harvests. They timed religious rituals, planned royal events, and made political moves. A ruler might choose a coronation date that aligned with a favorable combination in the Tzolk'in. Scribes recorded these events in stone carvings. You can still see them today on temples and stela across Central America. One carving might show a date like 9/12/2016, which experts can convert into our modern calendar. This system wasn't guesswork. It was based on close observation. Mayan astronomers tracked the paths of Venus and the Moon. They adjusted ceremonies to match eclipses and solstices. Their records show they understood these cycles with great accuracy, all without telescopes. They used math, patience, and a deep respect for the sky. Some indigenous cultures see time in a way that is very different from the way many people do today. Instead of thinking of time as a straight line, they see it as a circle. In this view, time doesn't move forward from past to present to future. It moves in cycles. Days, seasons, and years repeat. Life itself follows a pattern that returns to where it started. This view affects how people live, how they make choices, and how they understand their place in the world. Take the seasons as an example. In many indigenous traditions, the year is not just about counting months. It is about how the land changes and how people should act during those changes. Spring might mean planting. Summer means growing. Fall brings harvest. Winter is for rest and stories. These aren't just tasks. They are part of a larger rhythm. People act in ways that fit with the world around them. That rhythm repeats, so time feels like it comes back, not like it disappears. Ceremonies and rituals often follow these same patterns. A certain time of year brings certain actions. A solstice, a harvest, or a migration can call for song, dance, or prayer. These events are not just memories or traditions. They are ways to stay in step with the cycle. The story of a people gets told again and again, not as history, but as part of what is happening now. Some cultures use symbols like the medicine wheel to show how time and life work together. The wheel is not a clock. It shows how stages of life, birth, youth, adult, elder, move in a circle. One phase leads into the next, but also back into the first. An elder shares knowledge with the young, just as the young once received it from elders. This back and forth movement keeps the culture strong. In this view, time is not a race or a resource. It is not something to manage. It is something to live within. People belong to time as much as they belong to the land. This way of thinking does not try to control time. It listens to it. Western culture tends to see time as a straight line. It moves from the past through the present and into the future. Most people think of events as happening once and then being done. For example, a birthday happens once each year, and then it is over until the next one. This way of seeing time shapes how people plan, how they talk, and how they live. In many Western workplaces, this view shows up in schedules and deadlines. A meeting might start at 9 a.m. and end at 10 a.m. Everyone is expected to be on time, and things often move in order. One step leads to the next. If a report is due on Friday, the idea is to finish it and move on. This kind of time is measured, tracked, and divided. People often feel pressure to make the most of their time because it is seen as something you can lose. This view of time also shapes how people think about life itself. A child grows up, goes to school, starts a career, retires, and then gets old. Each stage follows the next. This pattern leads people to focus on goals and outcomes. Success means reaching certain points by a certain age, getting a job by 25, owning a home by 35, and so on. If someone takes a different path, others may see them as behind or off track. The way people speak also reflects this thinking. Phrases like time is money or don't waste time show how much value Western culture places on time as a resource. People often say things like looking forward to the weekend or put the past behind you. These sayings reflect the idea that time moves in one direction. In contrast, some other cultures view time as circular or flexible. But in Western settings, especially in the US and parts of Europe, the idea of time as a straight line affects daily life. It shapes everything from how people plan their days to how they think about their lives, whether at work, at home, or in school. This mindset is hard to avoid. In many ancient societies, the way people understood time looked nothing like the system we use today. They didn't split the day into 24 hours or track minutes on a clock. Instead, they used natural cues from the environment. The sun's position in the sky, the length of shadows, and patterns in the stars helped them track the passage of time. For example, when the sun rose, it marked the start of the day. When it reached its highest point, that meant midday. When it set, the day ended. These were the basic markers most people relied on. Egyptians developed a more structured system using sundials. These early timekeepers divided the daylight period into 12 parts, but these parts changed in length depending on the season. During summer, daytime hours were longer, and during winter, they were shorter. There were no fixed 60-minute hours. Instead, time flowed with the rhythms of nature. At night, Egyptians used water clocks, which measured time based on the flow of water from one container to another. This method gave a steady passage of time, but it still didn't reflect the minute-by-minute breakdown we use today. In ancient Greece, thinkers like Hipparchus started to explore more precise ways to divide time. He proposed splitting the day into 24 equal parts. Even so, this was more of an idea than a practical tool. Most people still used the sun and shadows for their daily activities. Farmers worked from sunup to sundown. Merchants opened their stalls when the market filled with people. Priests held ceremonies at certain points in the solar or lunar cycle. There was no pressing need for clocks that measured seconds or minutes. The Roman Empire used sundials and water clocks too, but the concept of fixed hours didn't spread far beyond elite circles. Common people did not carry watches or track appointments to the minute. Their lives followed the cycles of light and dark, feast and fast, planting and harvest. A person might say something would happen when the sun is high or after the third bell, but not at 3:15 p.m. Time was flexible, tied to lived experience rather than strict measurement. The modern way of thinking about hours and minutes took shape much later, only after mechanical clocks became common. Before that, most people moved through their days by watching the sky. Medieval clocks often only had one hand. These early timekeepers showed the hour, but not the minute. People didn't need to track time as closely as we do now. Most daily life followed the sun. Farmers began work at dawn and stopped when it got dark. The exact minute didn't matter, so clocks didn't try to show it. Churches were some of the first places to use public clocks. These clocks helped signal prayer times. Bells rang at regular hours to call people to worship. The sound was more important than seeing the time. If someone looked up at the clock face, they saw a single hand pointing to an hour mark. That was enough. Most of these clocks were mechanical. They used gears, weights, and escapements. These parts worked together to move the hand around the clock face once every 12 hours. It took skill to make these machines. Clockmakers had to understand ratios and motion. But even with that skill, the clocks were not very accurate by today's standards. A clock might drift by several minutes each day. But again, in a world where time moved with the sun, that was not a problem. You might imagine a market square in the 14th century. The town has a tower with a clock. The hour hand points to 2. That tells people it's early afternoon. A baker might glance up and know he has time to finish his bread before sunset. A merchant might pack up his stall soon. No one expects the clock to show 2:17 or 2:23. Just knowing it's the second hour after midday is enough. As life became more structured, people began to want more precision. Cities grew, trade increased, and people traveled more. Schedules became tighter. Eventually, clockmakers added a minute hand. That didn't happen all at once. It took centuries. But for much of the medieval period, one hand was plenty. The clock showed what people needed to know and no more. That fit the world they lived in. In ancient Rome, courts used water clocks to keep track of time during trials. These clocks, called clepsydrae, helped control how long someone could speak. Roman law valued order, and timing speeches was one way to keep things fair. A water clock worked by letting water drip from one container to another. The flow was steady, so people could measure time based on how much water had moved. Once the water ran out, the speaker had to stop talking. Roman trials followed a clear structure. Each side had a turn to speak, and they didn't get unlimited time. Instead of using hours or minutes, they divided the day into equal parts. If a trial was scheduled for 1/10 of the day, then each party got their share of that time. The water clock measured it out. This system made the court more efficient. It also stopped people from using long speeches to confuse the issue or wear down the judge. Imagine a courtroom in the Forum, the busy heart of Rome. A magistrate presides. One man steps forward to accuse another of breaking a contract. The accuser begins his statement. Beside him, an assistant watches a jar as water slips through a small hole. That's his clock. The defendant listens, waiting for his turn. When the jar empties, the accuser must stop. Then, the water is poured again, and the defense begins. No one interrupts. The clock does not pause, even if the speaker hesitates. These water clocks varied in size. Some were small enough for short statements. Others were larger, used in longer proceedings. The design could be simple. 2 pots, one higher than the other, joined by a narrow spout. Still, the system worked. It gave structure to arguments and reminded everyone that time, like justice, had limits. Lawyers had to plan their words well. They couldn't ramble or go off topic. A missed point meant a lost chance. Rhetoric mattered, but so did timing. If a lawyer tried to manipulate the clock, say by clogging the hole to slow the flow, it was seen as dishonest. Roman courts punished such tricks. The clepsydra stood as a quiet judge, taking down each word, shaping the rhythm of Roman law. Before trains crossed great distances, time didn't need to match from place to place. Each town set its clocks by the sun. Noon was when the sun was highest in the sky. That worked fine when most people stayed close to home. Travel was slow. Communication was slower. No one noticed or minded if the time in one town was 10 minutes off from the next. But railroads changed that. Trains moved faster than anything before. They carried people and goods hundreds of miles in a single day. Timetables became important. Railroads had to know when a train would leave one station and arrive at another. Conductors had to keep a schedule. Passengers expected it. A 10-minute difference between 2 cities could now mean a missed train or a crash. Accidents started to happen. One well-known crash happened in 1853 in Rhode Island. 2 trains were on the same track heading toward each other. The schedules said they should have passed each other safely, but the clocks at the stations didn't match. The result was deadly. People began to see that having no standard time was more than just an inconvenience. It was dangerous. Railroads began to push for change. They needed a better system. By the 1880s, major railroads in the United States agreed to divide the country into 4 time zones. Each zone kept a single standard time. This was known as railroad time. It wasn't a law. The government hadn't made it official yet, but the railroads had the power to make people follow it. If you wanted to catch the train, you had to use railroad time. On November 18th, 1883, the system went into effect. That day became known as the Day of 2 Noons. Some towns changed their clocks forward or backward by several minutes to line up with the new zones. In some places, people argued over it, but the trains ran on time. That mattered more than tradition. Soon, people got used to the change. Standard time became part of everyday life. The US government didn't make it official until 1918, but by then, most of the country already followed it. The railroads had made timekeeping essential. Without them, the push for standard time would have taken much longer. Before the Industrial Revolution, people measured time by the sun, the seasons, and their tasks. A farmer rose with daylight, worked until dark, and rested when needed. Time was flexible. It moved with the rhythm of nature and the body. People didn't track minutes or hours. Instead, they followed the needs of their work, whether it was planting, harvesting, or caring for livestock. Life followed a pattern, but not a rigid schedule. This changed with factories. Industrial machinery needed workers to start and stop at the same time. Factory owners didn't care if it was foggy or sunny. They cared if the machines sat idle. To keep production steady, everyone had to arrive on time, take breaks at fixed moments, and leave at the bell. Clocks became tools of control. Managers used them to monitor workers and to reduce wasted time. Time became something people owed, not something they used freely. The workday became a set unit. For example, a mill worker might start at 6 o'clock a.m., stop for a 30-minute break at noon, and finish at 6 o'clock p.m. Bells rang to mark each shift. If you were late, you lost pay or got fired. This system didn't care if you had to walk 3 miles or if your child was sick. It demanded punctuality. The habit of watching the clock entered daily life. People began to organize the rest of their day, meals, chores, even sleep, around their job's hours. School systems followed the same model. Children learned to sit still, follow instructions, and move on the bell. This prepared them for factory life. The classroom became a place to learn discipline as much as math or reading. Children grew up knowing that time belonged to someone else. The clock ruled both work and rest. This shift didn't stop with factories. Railroads needed exact timetables. Stores opened and closed at set hours. Offices scheduled meetings by the minute. Even leisure time became structured. You bought a ticket for a 7 p.m. show or met friends at 5:30 p.m. for dinner. Time no longer bent to the task. People bent to the clock. This new discipline shaped behavior. It taught people to hurry, to wait, to plan ahead. The Industrial Revolution didn't just build machines. It built the habit of timekeeping into everyday life. Some languages don't mark time the way English does. In English, we talk about events using past, present, and future tenses. We say things like, I went, I go, or I will go. These verb forms give a clear timeline. But not every language works this way. Some use the same verb form no matter when something happens. This changes how people who speak those languages think and talk about time. Take Mandarin Chinese. The verb doesn't change to show tense. You might say, I eat, whether you mean now, yesterday, or tomorrow. Instead of changing the verb, Mandarin speakers rely on time words like yesterday or tomorrow to give context. The sentence, I eat rice yesterday, would be understood as past tense because of yesterday, not because the verb changed. Time is external to the verb. This way of speaking shapes how speakers see time. If your language doesn't push you to separate past and future in grammar, you may not think of time as divided up in the same way. You might treat the future more like the present. Some researchers suggest this even affects behavior. In languages without future tense, people tend to save more money, smoke less, and make long-term plans. The idea is simple. If you speak about the future the same way you speak about the present, you may feel it's closer and more real. There's another example in Hopi, a Native American language. Hopi doesn't mark tense the way English does either. It focuses more on whether the speaker knows something to be true. You don't say it rained unless you saw it. If you heard it from someone else, you say that instead. This changes what's important. It shifts the focus from when something happened to how you know about it. Think of it this way. In English, a weather report might say, it will rain tomorrow. In a language without future tense, the speaker might say, rain comes tomorrow, using a present form with a time word. The rain feels more certain, more present. The future is not some distant, different state. It's just another point along the way. This doesn't mean these languages lack the idea of time. All people experience time, but how we speak about it affects how we organize our thoughts and actions. When grammar treats time as a side note instead of a main feature, it invites a different way of seeing the world. A Planck time is the shortest slice of time that still has physical meaning. It comes from quantum physics and shows how far we can go when measuring time. 1 Planck time is about 5.39 times 10 to the negative 44 seconds. That's a decimal point followed by 43 zeros and then a 5.39. It's so small that it's hard to compare to anything in daily life, but we can try. Imagine light, which is the fastest thing in the universe. In light travels around the Earth almost 8 times. In 1 Planck time, light would travel a distance so tiny it's almost nothing. Just 1 Planck length, which is about 1.6 times 10 to the negative 35 meters. That's much smaller than a proton. It's hard to picture, but it helps show how small this unit is. Scientists didn't come up with the Planck time for fun. It comes from real math. When Max Planck worked on black-body radiation, he used the speed of light, the gravitational constant, and the reduced Planck constant to come up with a set of natural units. These units are based only on physical constants, not on any man-made measurements like the second or the meter. Planck time is one of those units. At very early times in the universe, right after the Big Bang, things were so dense and so hot that our normal physics breaks down. This is where quantum gravity might come. We don't yet have a working theory of quantum gravity, but many researchers think that below the Planck time, space and time might not act like we expect. Space might not be smooth. Time might not be continuous. In this sense, the Planck time is a boundary. It's not just tiny, it's a limit to what we can talk about with current physics. No one can measure a Planck time with today's tools. It's too small, and we may never measure it directly, but it gives us a scale to think about where quantum mechanics and gravity start to meet. That's why the Planck time matters. It points to a deeper layer of reality, even if we don't fully understand it yet. Time moves slower at your feet than your head. That sounds odd, but it's true. The reason has to do with gravity and how it affects time itself. This isn't science fiction. This is part of Einstein's theory of general relativity, and it's been tested many times in the real world. Gravity bends space and time. When you stand on Earth, gravity pulls you toward the center of the planet. That pull is slightly stronger at your feet than at your head, because your feet are closer to the center. According to Einstein, this stronger pull makes time move a little slower. The difference is tiny, but it's there. You can't feel this effect, it's far too small. But atomic clocks can. These are the most accurate clocks we have. In one experiment, scientists placed two atomic clocks just 1 foot apart, one slightly higher than the other. Over time, the higher clock ticked just a bit faster than the lower one. The difference was about 90 billionths of a second over a year. That's not much for daily life, but it's enough to notice with precise tools. This matters more than it sounds. GPS satellites orbit Earth at high altitudes, where gravity is weaker. That means time runs faster for the clocks on the satellites compared to those on the ground. The engineers who built the GPS system had to account for this. Without adjusting for these time differences, GPS would be off by miles within a day. Think of standing on a mountain. Time runs just a bit faster there than it does at sea level. If you lived your whole life at the top of Everest, you'd age a little faster than someone who spent the same years on the beach. Not enough to notice, but enough that the math checks out. This isn't just about mountains or satellites. It's true for everything with gravity. Black holes have such strong gravity that time almost stops near them. We see this effect play out across space, not just here on Earth. Time and gravity are linked. You're aging slightly faster at your head than your toes. That's not a guess, that's physics. Astronauts on the International Space Station age a little slower than people on Earth. This difference is due to how time works when you move very fast or when you're in a weaker gravitational field. It's a real effect, even though it's very small. It comes from Einstein's theory of relativity. That theory says time moves at different speeds depending on how fast you're going and how close you are to a large mass, like Earth. The ISS orbits Earth at about 28,000 kilometers per hour. That speed causes time to pass more slowly for the astronauts compared to someone standing still on the ground. This part is called time dilation due to velocity. But the station is also farther away from the center of Earth than people on the ground. That means it's in a weaker part of Earth's gravity. According to relativity, being farther from a strong gravity source makes time move a bit faster. That's called gravitational time dilation. These two effects work in opposite directions. The fast speed slows time down. The weaker gravity speeds time up. On the ISS, the speed effect wins. So astronauts there age more slowly, but only by a tiny bit. Over 6 months, they might age about 0.005 seconds less than someone on Earth. You wouldn't notice it without precise instruments. But scientists have measured this difference. To picture it, think about twins. One stays on Earth. The other spends 6 months on the ISS. When they reunite, they look exactly the same. But if you used atomic clocks to track each of them, the twin on the ISS would be a fraction of a second younger. That's not enough to make someone live longer in any practical sense, but it proves time doesn't move the same everywhere. NASA has looked into this effect closely. In the twin study, astronaut Scott Kelly spent almost a year on the ISS, while his twin, Mark Kelly, stayed on Earth. They studied how his body changed, and though the time dilation was small, it lined up with theory. Their DNA didn't change from time dilation, but it showed how long-term spaceflight affects humans in many ways, including time itself. Some turtles perceive time more slowly than humans. This doesn't mean time itself changes. Instead, it means their brains process changes in the environment at a different speed. To understand this, imagine how you see a ball flying toward you. You might be able to track it and catch it. A turtle might see that same ball move more slowly, as if in a slowed-down video. This happens because of how fast or slow the brain takes in visual information. Scientists call this temporal resolution. Temporal resolution varies from species to species. It depends on how quickly the brain can take in snapshots of the world. Think of it like a camera. Some cameras take 60 frames per second. Others take 30. A turtle might see the world at a slower frame rate than a human. But in some cases, the opposite happens. Certain turtles process vision at a faster frame rate than us, allowing them to detect quick movements in water that we would miss. Researchers tested this by flashing lights at different speeds. They checked when animals could no longer tell the flashes apart. At some point, the light seemed steady instead of blinking. That threshold tells us how fast the animal processes visual data. Turtles showed slower thresholds than many mammals. That means their brains notice fewer changes per second. But this slower pace could help them see details in slow-moving environments, like still water or sandy bottoms. A slower sense of time might also change how turtles experience movement. A human walking past a turtle might seem like a blur, but to the turtle, it could feel drawn out. This perception shapes how turtles respond to threats. If a predator moves fast, a turtle's slower visual system might not process the danger in time to react. Still, not all turtles are the same. Sea turtles, for example, need to respond to fast currents and other fast-moving animals. Their time perception may differ from that of land turtles, which move and live more slowly. The way each turtle species sees time connects closely to its habitat and daily behavior. Time perception isn't fixed. It's tuned to fit the needs of each animal. A fly zips through the air, dodging swats and sudden movements with ease. To a person, it looks like luck or incredible reflexes. But from the fly's perspective, everything moves slower. This isn't a trick of eyesight, it's how their brains process time. Flies, like many small animals, perceive time differently from humans. Their visual system refreshes faster, which means they take in more images per second. In a way, it's like watching the world in slow motion. The science behind this involves something called critical flicker fusion rate. It measures how many flashes of light an animal can detect in 1 second before the flashes blend into a constant beam. humans average around 60 flashes per second. Flies can see over 200. This means they're catching details that humans miss entirely. When someone swings a hand to swat a fly, the motion may seem quick, but to the fly, the hand crawls forward like a slow wave. That gives it just enough time to jump or fly away. Think of it like watching a slow motion replay during a sports game. Everything is easier to follow. You see a baseball spinning mid-air or a player's foot meeting the ball. For a fly, normal life happens at that pace. This helps explain why they're so hard to catch. They react before most people realize they've moved. The fly's nervous system plays a key role here. Its eyes detect fast changes in the environment and send signals to the brain. The brain responds almost instantly. The fly's muscles are small, so they don't need much time to move. Insects like flies don't spend energy on thought the way humans do. They rely on built-in responses. If something looks like danger, they take off. Other small animals show similar traits. Hummingbirds, for example, also have fast vision and movement. It helps them avoid predators and steer through tight spaces while flying. The rule seems to be, the smaller the animal, the faster their internal clock runs. This gives them an edge in survival, especially when danger moves in large, slow shapes like people. Time reversals are used in quantum experiments to explore how particles behave when time appears to run backward. In classical physics, time moves forward, and most events follow a simple cause and effect pattern. Drop a glass, and it shatters. You don't expect the shards to leap back into place. But quantum mechanics doesn't always follow the rules we see in everyday life. In a quantum system, particles don't have definite positions or paths unless measured. Instead, they exist in a range of possible states. When scientists use time reversals, they take advantage of the fact that the math behind quantum mechanics often stays the same if you reverse the direction of time. This means that, at least on paper, some processes can be run backward. In a real lab, scientists can't make time run in reverse, but they can simulate it. They do this by applying a set of operations that undoes the effects of a prior step. For example, if a group of atoms is placed in a magnetic field that causes their spins to change in a certain way, scientists can reverse the magnetic field to drive the spins back to their earlier state. This reversal mimics what it would look like if time moved backward for those particles. One famous experiment used a quantum computer to simulate time reversal. Researchers prepared a small system of qubits, quantum bits, and evolved them forward using a specific set of operations. Then they applied a new sequence that mathematically reversed the earlier steps. The system returned to its starting state, as if time had rewound. This didn't break any laws of physics, but it did show how quantum information can be manipulated with extreme precision. These reversals help researchers understand how fragile quantum systems are. Even small errors or noise can keep the system from fully returning to its earlier state. That tells scientists how much control they need to maintain over the particles and fields involved. It also reveals how information spreads and gets scrambled in quantum systems, which is important for building quantum computers and understanding black holes. Time reversals aren't about making science fiction real. They're tools. They help researchers test ideas about entanglement, decoherence, and the flow of quantum information. By simulating backward evolution, they can see how systems respond and how far the math holds in real conditions. In video games, bullet time slows down the action to help players react to fast-moving events. The screen blurs, sounds stretch out, and everything moves in slow motion. This feature doesn't just look cool. It mimics how people say time feels when something intense happens, like a car crash or a near miss. In real life, many people report that time seemed to slow down during a crisis. They say they could notice small details, make fast decisions, or even think more clearly. One person might say they saw every twist of a car during a skid. Another might remember the sound of a single word during an accident, stretched out like a long note. Scientists call this perceived time distortion. Games use bullet time to give players that same feeling. When used well, it makes the game more engaging. It gives players a second to think, aim, or dodge. In a first-person shooter, for example, a player might hit a button to enter bullet time just before a grenade explodes. The camera zooms in slightly. The screen tints blue. The grenade floats through the air like it's underwater. The player has enough time to run behind cover or shoot an enemy before the blast. Developers add this effect by slowing down the game's internal clock while keeping controls responsive. They often lower the pitch of sound effects to match the slow pace. They might add visual effects like motion blur or depth of field to make the moment stand out. The slowdown has to feel smooth, not clunky. If it lags or looks off, it breaks the illusion. Games like Max Payne, Fear, and Red Dead Redemption 2 use bullet time to help players manage tough fights. In Max Payne, bullet time became central to the story and mechanics. The player, outnumbered and outgunned, could dodge bullets in slow motion and return fire with more accuracy. It wasn't just a gimmick, it fit the tone of the game, a man caught in a gritty, high-stakes world. Bullet time doesn't just make the game easier, it makes the player feel sharper. It mirrors what the brain might do when facing real danger. Slow things down to buy a moment of clarity. Games give players that moment on demand. When you open your eyes and look around, you think you're seeing the world as it is. You aren't. What you're seeing already happened around 100 to 200 milliseconds ago. That's about 1/10 to 1/5 of a second. Your brain needs that time to gather the raw data from your eyes, process it, and turn it into something you can understand. But you don't notice the delay. You never feel behind. That's because your brain hides it from you. To keep things smooth, your brain blends what just happened with what it expects to happen next. You experience a version of reality that's edited to feel live. It works like a video stream with buffering. The delay is real, but the content looks smooth because your brain fills in the missing parts using prediction. Imagine watching someone throw a ball. The ball leaves their hand, travels through the air, and lands in a glove. That takes time, but your brain tracks it as if it's happening now. It relies on signals from your eyes, ears, and memory of similar events. It guesses the ball's path before it lands. If the guess is right, everything feels real time. If it's wrong, you may notice something odd, like when a ball takes a strange bounce, or someone fakes a throw. Now think about what this means. Everything you see is a little old. When someone raises an eyebrow or shifts their weight, your brain picks it up late, yet you respond as if it's instant. You keep a conversation going, play sports, drive in traffic, all based on guesses that feel like facts. This delay doesn't only happen with your eyes. It affects hearing, touch, and movement too. When you clap your hands, you feel the impact and hear the sound, but those signals take different paths to your brain. One moves faster than the other. Your brain lines them up to make it feel like they happened at once. It edits your senses for consistency, not accuracy. You never notice the lag because your brain does the editing behind the scenes. It makes you think the lights flick on the moment you hit the switch, or that you're reacting to someone's words as soon as they speak. But really, you're reacting to something already over. You live just behind the present, walking through a world that already happened, stitched together to feel seamless. You don't experience the world in real time. Every moment you think you're living in is already half a second old. Your brain delays your awareness by about 500 milliseconds. That's long enough to change everything about how you think the world works. You touch a hot stove and pull your hand back. You think the pain caused the motion. It didn't. Your brain already sent the signal to move before you felt the burn. The feeling arrives late, like a voice message played back after the conversation. The movement was reflexive. Your awareness came after. You see a ball flying at your face. You duck in time and think, "Good reflexes." But your body began to move before you saw the ball, at least before your conscious mind did. The information hit your retina, went through your brain's visual processing centers, and set off motor commands. That all happened before you became aware of the ball. The brain stitches the world together and feeds it to you with a delay. It fills in gaps. It smooths over inconsistencies. If someone flashes a light to your left and taps your right shoulder at the same time, you think both happened together. But if you look closely at the timings, you'll find that your brain fudged the order to keep things neat. It prioritizes a stable story over accurate timestamps. This isn't a bug, it's a feature. If you had to wait for perfect information, you'd never catch a ball, dodge a punch, or finish a sentence. The delay lets your brain process raw signals, predict what will happen next, and package everything into a clean, smooth story. That story is what you call consciousness. Some parts of your brain live in the now. They fire muscles, process sounds, react to changes. They work with current data. But the part that tells you who you are, what you see, and what just happened, that's the part that lags behind. It's always watching a highlight reel, never the live game. So every time you think you're acting in the moment, you're actually watching the past. The brain made a decision, sent a signal, and let your conscious mind catch up just in time to take credit. Time can be measured using light pulses in quantum systems. This method relies on how light interacts with atoms or particles. In simple terms, scientists use short bursts of light to track changes in a quantum state. These changes happen at very small timescales, far smaller than what we can see or feel. One common setup uses an atom or ion held in place by electromagnetic fields. A laser sends a pulse of light at the atom. This pulse pushes the atom into a different energy state. After a set amount of time, another pulse checks if the atom stayed in that new state. The results show how much time passed between the pulses. By repeating the experiment many times, researchers can measure time with great precision. This works because atoms in a quantum system behave in predictable ways. When light hits an atom, it can excite electrons to higher energy levels, are unique to each kind of atom. Scientists know how much energy each level holds. When the electron falls back down, it gives off light. The color of that light tells researchers how much energy changed hands. Since energy and time are related, the system becomes a very fine clock. For example, a type of clock called an optical lattice clock uses strontium atoms. It traps the atoms in a grid made of laser beams. Each atom sits in one spot. Like an egg in an egg carton, lasers hit the atoms and track their response. These clocks can measure time so precisely that they would not lose a second for billions of years. Another example involves using photons in an interferometer. Light splits into two paths and then comes back together. The time difference between the two paths creates a pattern. This pattern tells how much time has passed. Even tiny shifts in the pattern can mean a change in time measured in femtoseconds or smaller. These systems don't use gears or springs. They use particles and waves. That makes them stable and accurate. It also means they can keep time even in places where traditional clocks would fail, like in space or near very strong gravitational fields. The question of whether time is fundamental or comes from something deeper like space is one of the biggest puzzles in physics. There isn't a clear answer yet, but we can look at the ideas behind both sides. In classical physics, time is treated as a background. It flows evenly, like a clock ticking. Events happen in order, and we measure how long they take. Space is the area where things happen, and time tells us when they happen. This view comes from Isaac Newton. He thought time and space were separate and absolute. Albert Einstein changed that. His theory of relativity shows that space and time are not separate. They form one thing, spacetime. In this view, time depends on how you move and where you are. For example, if two people are moving at different speeds, their clocks won't agree. Time slows down near heavy objects like black holes. So time in this case is not a fixed thing. It changes based on space and motion. This idea suggests time might not be fundamental. It could be part of a larger structure that includes space. Quantum physics adds more questions. In quantum mechanics, we usually assume time flows smoothly. But in theories that try to combine quantum physics with gravity, like quantum gravity, time starts to look strange. Some versions of these theories don't include time at all in their basic rules. Instead, they describe how one state turns into another without needing a clock. One example is the Wheeler-DeWitt equation. It's a key part of quantum gravity research. That equation doesn't have time in it. The system evolves, but there's no T to plug in. This leads to the idea that time might emerge from other things. Just like temperature comes from how atoms move, time might come from how the state of the universe changes. Think of a forest. From a distance, it looks green and smooth. Up close, you see individual trees. Time might be like that. It looks smooth, but it may come from something more detailed and complex. Some physicists think that what we call time is just our way of organizing change. The universe moves from one configuration to another, and we call that change time. But the change could exist even if there's no clock ticking in the background. This debate is ongoing. Different models of the universe say different things. Some suggest time is built in, like space. Others say it's a feature that shows up when you look at the world a certain way. We don't yet know which view is right. But exploring these ideas helps us understand the rules that shape everything around us. We see time move forward every day. The sun rises, then it sets. We get older. A glass falls, it breaks. We don't see a broken glass leap off the floor and put itself back together. These small events show us something bigger. Time seems to flow in one direction. But why does it move forward, not backward? The key idea here is entropy. Entropy is a measure of disorder in a system. Over time, entropy tends to increase. You can think of it like this. If you open a jar of ink in water, the ink spreads out. It doesn't gather itself back into the jar. That would be a decrease in entropy. But nature prefers disorder, so things move from neat to messy. This is a rule in physics called the second law of thermodynamics. This law doesn't say time must go forward. Instead, it says that in systems where entropy increases, we notice time going forward. Imagine a film reel. If you watch a glass shatter and then play it backward, you can tell it's in reverse because you know what usually happens. Our sense of time's direction comes from seeing cause and effect linked to growing disorder. What's strange is that many physical laws work both ways. You could reverse the math, and the laws would still hold. Gravity, for example, doesn't care which way time runs. Same with Newton's laws of motion. But the second law of thermodynamics does care. It points in one direction. That makes it special. Let's say you put an ice cube in a cup of hot coffee. Over time, the ice melts, the cold spreads into the coffee, and the whole cup becomes lukewarm. That's entropy at work. If time moved backward, you'd see the water separate, cold gather into a cube, and the coffee get hot again. But we don't see that. We only ever see things move toward more mixed states. Our brains play a role too. We remember the past, but not the future. That means we collect knowledge in one direction. That's because our memories are physical systems, and they follow the same rules of entropy. As time moves forward, our brains store more information. If time moved backward, we wouldn't know what came before. So, time feels like it moves forward, because that's the way disorder increases. The universe started in a very ordered state, and it's been getting messier ever since. Every clock tick, every breath, every melted ice cube points the same way. Time might be infinite. We don't know for sure. What we do know is that time as we understand it started with the Big Bang. Before that, we can't say much. Our tools and ideas break down when we try to look past that point. But after the Big Bang, time has kept moving forward. Clocks tick, stars form, planets spin, and people age. Time moves in one direction. That's the arrow of time, tied to entropy. As things become more disordered, time goes forward. If the universe keeps expanding forever, time could also keep going. Some models of the universe support that idea. In these models, galaxies will drift apart, stars will burn out, matter may decay. After trillions of years, there may be nothing left but cold particles spread far apart. But time, in theory, would still go on. Even in a cold, dark, empty universe, time would still tick. No one might be around to measure it, but it would keep moving. There's another option. The universe could stop expanding and start shrinking. That's the big crunch theory. If that happens, time might have a limit. Maybe time would run in reverse as the universe contracts, or maybe it would just end. We don't know. No one has seen a universe collapse. We only have math and models. There's also talk in physics about time not being real at all. Some ideas suggest time is just a way we make sense of change. In these views, time isn't something that flows. It's a label we attach to things so they make sense, but we treat it like it's real because it works. It lets us build machines, measure speed, and predict motion. Quantum physics adds another layer. In some versions, time doesn't play a central role. Things just happen, and time is part of how we describe the process. But again, we treat time like a real thing because it gives us useful answers. If we imagine time as a number line with 0 at the Big Bang, the line could stretch out forever. That's one way to picture infinite time. Think of sitting at a bus stop that never closes. Buses stop coming, people stop showing up, but the clock on the wall keeps ticking. No end, just silence and motionless change. That's one possible future. If you look around, it feels like there's a now. You check your watch, see the time, and say, "This is happening right now." But the universe doesn't really work that way. The idea of now is something we invented to make sense of what we experience. Physics doesn't give now any special meaning. Einstein showed us that time is not the same for everyone. In his theory of relativity, time depends on how fast you're moving and how close you are to something with a lot of gravity. Two people moving at different speeds can experience different flows of time. What's happening now for one person might already be in the past or future for someone else, depending on their motion and location. Imagine two astronauts. One is on Earth, and the other is on a spaceship moving very fast. For the astronaut on the ship, time ticks slower. If they both try to agree on what's happening right now, they can't. Each of them will measure a different set of events as happening at the same moment. That's not a problem with their clocks. It's built into how the universe works. We can't even say the universe has a single now. In everyday life, we assume all clocks tick at the same rate and that there's a shared present moment. But the universe is bigger and more complicated than that. The farther apart two events are in space, the harder it is to say which came first, or if they happened at the same time. You can even change the order of some events by moving in a different direction or at a different speed. That would be impossible if now were something absolute. Say you look up at a star 1,000 light years away. The light you see left that star 1,000 years ago. You see what it looked like long before your great-grandparents were born. If someone on that star looked at Earth right now, they'd see a version of it from 1,000 years ago. Their now and your now don't match up. In the universe's eyes, there's no single clock or shared moment tying it all together. Each place and observer carries their own version of time. Some physicists think the future already exists. This idea comes from a way of looking at time called the block universe. In this view, time is like a map. The past, present, and future all sit on this map at once. We move through it like a car moves along the road, but the road is always there. Just because we haven't reached a certain point yet doesn't mean it doesn't exist. This idea fits with Einstein's theory of relativity. In that, time is not the same for everyone. A person moving fast experiences time more slowly than someone who is still. So the idea of now is not universal. Your now might be someone else's past or future. That makes the idea of the present less special. It suggests that the past and future might be just as real as the present. Think about a film reel. The whole movie exists on the reel, beginning, middle, and end, even if you're only watching one frame at a time. In the block universe, our experience of time is like watching one frame after another, but all the frames are there. They don't vanish after we watch them, and they don't wait to be created. This doesn't mean we know what will happen. We still feel uncertainty. You can flip a coin and not know if it'll land heads or tails. But in this view, the outcome already exists somewhere in the future. You just don't know what it is yet. It's like having a sealed envelope with a message inside. The message already exists, even if you haven't opened it. Not all scientists agree with this. Some believe the future is open and gets built as we go. They think the present has a special role. In this view, time flows like a river, and we're on a boat drifting forward. The banks behind us are fixed, but what's ahead hasn't formed yet. But physics doesn't need the idea of a moving present. The laws work whether time flows or not. Equations treat time as just another dimension, like space. A ball's path through the air can be described fully with math, from the start to the end, without needing to talk about now. Whether we live in a block universe or not changes how we see choice, chance, and meaning. If the future is already there, then what we call decisions might just be part of the path, not steps we create. It's a deep and strange idea, but one that many physicists take seriously. Some scientists and philosophers have suggested that time might not be what we think it is. We often feel time moving forward. We watch clocks tick, we grow older, we remember the past, but not the future. These things seem to show that time flows, but maybe that flow isn't real. Maybe it's just how we experience the effects of entropy. Entropy is a concept in physics. It has to do with disorder. A low entropy system is neat and ordered. A high entropy system is messy. Over time, the entropy of a closed system tends to increase. This is part of the second law of thermodynamics. Ice melts, eggs break, buildings crumble. These are all examples of entropy growing. Now imagine a broken cup lying on the floor. We know that at some point it was a whole cup. Then it fell and broke. We don't expect to see the pieces jump back together. That's because moving from high entropy to low entropy is very unlikely. So we think of the whole cup as the past and the broken cup as the present. In this way, our sense of time may come from how entropy behaves. Our brains process memory by storing past events. Each memory is built out of chemical changes, physical records inside our heads. These changes only work one way. You remember what you had for breakfast, but you don't remember tomorrow's lunch. That's because the storage of memory itself relies on entropy increasing. We also make cause and effect connections. You light a match and then see the flame, not the other way around. These patterns line up with how entropy rises. Causes come before effects in systems where entropy grows. There are no known laws in physics that demand time must move forward. Most laws work just as well in reverse. But the second law about entropy points in one direction. That might be why time seems to flow the way it does. Think of a shuffled deck of cards. You see cards in no clear order. That disorder gives you clues. If you had seen the deck in perfect order, you would guess someone just opened it or sorted it. In this way, the state of the system tells a story. But the story only makes sense if entropy rises. Without that, you could not tell what came first. If we lived in a world where entropy didn't increase, our memories would not build up. Our actions would not lead to expected results. We might not feel time passing at all. Some people believe that all moments in time, past, present, and future, are equally real. This view is called the block universe. In this view, time works like space. Just as every place exists, even if you're not standing there, every moment exists, even if you're not living in it. The past hasn't gone away. The future isn't waiting to happen. They're both there, like different points on a map. Think of a film reel. Each frame shows a different scene. When you watch the film, you see one frame at a time, but all the frames exist at once on the reel. In a block universe, time is like that reel. You move through it moment by moment, but the reel doesn't change. Your experience changes, not the reel itself. You feel the present as special because your consciousness is in that moment. But in this view, your birth, your middle age, and your death all exist at once, just not from your current point of view. This idea comes from physics, not just philosophy. Einstein's theory of relativity shows that time is linked to space. What you see as now might not be now to someone else who is moving differently through space. This shakes the idea that the present is universal. If two people can't agree on what counts as now, then maybe now isn't something real on its own. Maybe all moments are equally real, and your sense of moving through them is just part of how your brain works. But not everyone agrees. Some argue that the future can't be real because it hasn't happened yet. They say only the past and the present are real. Others say only the present is real, what's called Presentism. In that view, the future is open and the past is gone. Still, the block universe fits well with modern physics. It helps explain why time appears to move in one direction, even though many physical laws don't care about direction. It also helps make sense of things like time dilation. where two clocks can tick at different speeds depending on how they move. If time were flowing like a river, it would be hard to explain how two people could disagree about what time it is. But in a block universe, they aren't disagreeing about the flow. They're just in different parts of the map. We feel time moving in a smooth, ongoing way because of how our brains process events and changes. Our brains don't work like cameras that take still pictures one after another. Instead, they take in a steady stream of information from our senses. They then organize this stream so we can understand what's happening around us in real time. This process works a lot like watching a movie. A movie is made of many still images shown quickly, one after another. On their own, the images don't move, but shown at the right speed, your brain fills in the gaps and sees smooth movement. Your brain does something similar with the events in your life. It connects the things you see, hear, and feel into one smooth experience. This linking happens very fast, within milliseconds. Your brain uses what's happening now, what just happened, and what it expects to happen next. It builds a picture of the present that feels complete. It fills in tiny gaps so you never notice a break, even when your eyes blink or your attention shifts. There's also something called the specious present. It's the short period of time your brain treats as now. It usually lasts a few seconds. During this window, your brain holds recent events together as if they are still happening. If you watch someone toss a ball and catch it, you see the motion as one event. You don't break it into pieces. That's your specious present at work. Memory also helps. You don't just live in the present. You carry short-term memory that lets you hold on to what just happened and link it to what's happening now. This gives your sense of time a flow. If someone says a sentence, you remember the words they just said, so the full meaning makes sense. If your memory broke after each word, you'd never follow the sentence. Let's say you're walking through a park. You see a dog run by, hear a child laugh, and feel a breeze on your face. All of this hits your senses in sequence, but your brain ties it together. You remember the start of the dog's run and expect where it will go next. You don't notice any gaps. The experience feels like a single moment, even though many small things happened. This smooth sense of flow is your brain working hard in the background. It filters, connects, and predicts, all to help you feel that time moves forward without a break. Time moves forward. Seconds tick by. Days pass. We grow older. But will time ever stop? That question pulls from physics, philosophy, and even imagination. To answer it, we need to look at how science defines time and what the universe might do in the distant future. In physics, time is part of space-time. That's the fabric that holds everything in the universe. It's not just something on a clock. It's linked to how things move and how gravity works. Einstein showed that time moves slower near strong gravity and faster when moving close to the speed of light. But no matter what, time always moves forward. We don't see it rewind. Still, some theories ask what might happen if the universe ends. That's when we get to the idea of time stopping. Right now, the universe expands, galaxies move away from each other. But what if that expansion stops? Some scientists think gravity might pull everything back in. A process called the Big Crunch. If that happens, the universe could collapse into a dense point. Some theories say time could slow and stop at that point. Others say it might reverse. We don't know. No one has seen it happen. Another idea is the heat death of the universe. If the universe keeps expanding forever, it will cool down. Stars will die. Black holes will fade. In the far future, maybe after 10 to the 100th years, there might be nothing left that changes. No movement, no light, no heat. just stillness. Some call that the end of time. But time wouldn't stop ticking. It just wouldn't matter anymore. Nothing would happen for time to measure. There's also a theory from quantum mechanics. It suggests time may not exist at all at the smallest scale. In loop quantum gravity, space and time come in small chunks. If time is not smooth but made of pieces, it might not flow the way we think. That doesn't mean time stops. It just means time could work in a different way than we experience. Even if everything stops changing and the universe reaches perfect stillness, our idea of time as a sequence of change might just fade. But unless the rules of physics change, time itself won't stop. It will just have nothing left to count. Time feels real. We see the sun rise, shadows stretch, people age, clocks tick. But the way we feel time, its flow from past to present to future, might not be a direct window into reality. It might be a tool built by evolution to help us survive. Think about it this way. Early humans needed to hunt, gather, avoid predators, and care for each other. These tasks all happen in a world where change unfolds in sequences. If you couldn't predict what came next, you were at a disadvantage. If you couldn't learn from the past, you repeated mistakes. Time perception gave structure to those sequences. It helped our ancestors connect cause and effect. Lightning flashes, then thunder. Step too close to the fire, and you feel pain. These aren't just events. They're part of a timeline the brain learns to recognize. This sense of time helped people plan. Someone who could remember how long a food source lasted would come back before it spoiled. Someone who could guess how long a task would take could manage energy better. Evolution favored brains that tracked patterns over minutes, days, seasons. We aren't born with clocks in our heads, but we build a rough one from our senses. A heartbeat, a footstep, the changing light. These become anchors. There's also memory. Without it, time wouldn't feel like it flows. You'd live in a series of disconnected moments, but memory strings moments together. It forms a sense of continuity. That's important for identity. You don't just act, you remember acting. That thread lets you learn, adjust, and make decisions. Still, perception isn't the same as reality. Physics tells us time isn't a fixed flow. In some equations, time looks symmetrical, meaning forward and backward are treated the same. But our brains don't process time like that. We move forward. We feel the weight of before and the unknown of later. This forward arrow of time feels hardwired, but it might just be a model we use to keep going. Imagine walking through fog with a flashlight. You see what's in front of you only as far as the light reaches. Behind you, you remember what you've seen. That's how time feels. Evolution gave us the flashlight, not the full landscape.